Hello, my name is Callie García, and today I'll be discussing evaluating the prospect of central engine activity in stripped envelope supernovae. So first of all, what is a supernova? Well, a supernova is part of the natural progression of the life cycle of certain stars, and supernovae generally form in one of two ways. Either a white dwarf gains enough mass that it reaches the Chandrasekhar mass limit and explodes, or a massive star runs out of nuclear fuel and no longer possesses the energy it needs to sustain itself under its own gravity, and its core collapses in on itself. And studying supernovae is useful for a variety of different reasons. First of all, as a common end-of-life process for a lot of stars, it helps to inform our understanding of the stellar life cycle. Additionally, supernovae are responsible for the production of many heavy elements heavier than iron, and so understanding supernova evolution can help inform our understanding of the formation of various elements and their redistribution back into the universe. Additionally, supernovae have a time-luminosity correlation that allows their light curves to be standardized, making them useful standard candles after some processing. And today I'm here to talk specifically about stripped envelope supernovae, which are a type of supernova that forms from stars that have lost their outer hydrogen-rich layers. And this process usually happens in one of two ways. Either they're Wolf-Rayet stars that have lost their outer layers from winds, or they're massive stars and binary systems that have had their outer layers stripped off by their partner star. And it's generally believed that their luminosity is powered by the radioactive decay of nickel-56. However, some people have argued that the luminosities that we record for stripped envelope supernovae are significantly higher than the energies that we would expect from nickel-56 alone. And they suggest that there must be some other energy contributing to the luminosities we see. And their two suggestions for what this could be are either circumstellar interference or some form of central engine activity like a magnetar that's driving these luminosities. So enter the Rodriguez 2024 paper, which was a paper published earlier this year, which evaluated 54 different stripped envelope supernovae that have been recorded to assess whether or not they could possess central engine activity. And the paper specifically selected for supernovae that did not have any indicators of circumstellar interference. Circumstellar interference has traces in spectra that we can select out for. And so this evaluated specifically for central engine activity. And evaluating the predicted energy from nickel-56 for each of these supernovae, which we'll get into, and comparing this to the luminosities recorded, the paper argued that they found substantial energy gaps for a significant number of the supernovae they evaluated, and therefore argued that this must indicate that there is central engine activity in stripped envelope supernovae. And they did this evaluation by using this equation, which argues that, which states that the energy change of a system is the energy that we expect from nickel-56 minus the luminosity that we actually see. So if luminosity is only being driven by nickel-56, then we expect that the energy change we see is zero. And Rodriguez et al. Argued that this was not the case for a substantial number. There were a substantial number of non-zero energy changes for the supernovae. And the equation evaluates the time-weighted luminosity and time-weighted energy change from nickel-56 using these two equations here. And this Q is the energy that we expect to see from nickel-56, which can be broken down further by this equation, which uses a variety of inputs that we get from observables from each of these systems. And it's worth noting that there are two free parameters in this system. There's a T-escape value, which is the escape value, the escape time of radiation from the system, and nickel mass, which explains itself. And so fitting for these parameters, the Rodriguez paper evaluates the overall energy that we expect to see from nickel-56 and takes the difference. And so our research goal is to replicate the Rodriguez methodology using a set of simulated light curves that do not have any central engine activity or circumstellar interference. We used a set of simulations that only treats nickel-56 as the sole driver of luminosity in stripped envelope supernovae to see whether or not we get these same energy gaps, and if so, then central engine activity might not be the cause. And so we do this using Sedona, and Sedona is a Monte Carlo code that uses radiative transfer properties to simulate supernovae. The code treats nickel-56 as the sole driver of luminosity, so it serves as a useful constraint as we're going about this. And we, using the free parameters of T-escape and nickel mass, use the Rodriguez et al. Equation to fit to the light curves. We use 99 simulated Sedona light curves to fit to later times. And we fit these equations for energy from nickel-56 to later luminosity times, specifically after 60 days, because before this time, the material that we're observing is optically thick and therefore is not anticipated to accurately reflect energy from nickel-56. Around 60 days and beyond, it should be an accurate fit, and so we fit to this time. And once we fit to this time, using these same Rodriguez equations, we assess the final luminosity, the final time-weighted luminosity, and the final time-weighted energy from nickel-56, and taking this difference is our metric of whether or not there's a substantial energy gap between the two. And you can see here that for this one, there's a non-zero energy gap, which the Rodriguez paper would argue points to central engine activity, if this is a system where there is no known lack of a central engine. And so our results found that there was actually a very large scatter between differences between nickel-56 energy and recorded luminosities. So you can see that there is a substantial peak around 0, so that there's no gap between these, but there's also a fair amount of sprawl. We get actually about 50% of our values have a negative distribution, which is interesting because the Rodriguez paper has no non-zero values. No non-zero values, meaning that the luminosity is always less than what we would expect it to be from nickel-56. Whereas with the Sedona light curves, about 50% of the time, the luminosity is greater than what we would expect it to be from nickel-56 alone. And it's worth noting that with Sedona, we see a handful of supernovae that have differences of about 40%, which is actually greater than the differences that Rodriguez et al. Is using to argue that there's a substantial enough energy gap that we see there must be central engine activity. And we know that these 40–45% energy gaps are coming from a system with no central engine activity, with only the radioactive decay of nickel-56 driving luminosity. And therefore, we can say that we did successfully find significant energy gaps without central engines, and therefore, large energy gaps alone are not necessarily an implicator of central engine activity, like the Rodriguez paper argues. Some potential sources of error in this work include the fact that we calculated time-weighted luminosity at final times instead of at 100 days. For Sedona simulations, they generally end around the 80 or 90-day mark, and rather than inferring the last 10 to 20 days, we decided to take it at final times. The Rodriguez paper in their methodology takes the time-weighted luminosity at 100 days for every supernova, whether or not its light curve continues out to 100 days. For some light curves, they drop off or they stop recording data, and the Rodriguez paper uses mathematical inference to predict what those values would be at 100 days. To try and avoid relying on mathematical inference and to rely on hard data alone, we took the data gaps at final times. But it's worth noting that if our mathematical inference was accurate enough, the difference between energy from nickel-56 and luminosity should be the same regardless of whether we take it at the final time or at 100 days. We could also begin by comparing the energy difference, the energy gaps recorded from our fit of nickel mass to what we know the input of nickel mass to be to the various Sedona models to see whether or not that affects the energy gaps that we recorded. And we can also evaluate, and we hope to look into what is different in the Sedona simulations that have larger energy gaps to see what about these could be setting them apart, if not central engine activity. And I would like to thank Professor Ashley Villar, Karthik, Alyssa Goodman, Doug Finkbeiner, the Astro98 cohort, my dean, and my family.
Time for questions. Thank you very much. So, questions? Charles.
So the data on the supernova that's going to study, are they collected by one organized group, or are these taken from many different sets of reporters?
As I understand it, they were collected by the same authors of this paper, by Rodriguez et al.
Oh.
So what are you going to say to Rodriguez et al?
That's a great question that I'll have to discuss with Professor Villar.
John.
What's the distribution of iron 56 energy release in all supernovae that have been studied? How broad a feature or how narrow a feature is it?
I'm sorry, could you rephrase the question?
Well, you're using the total energy in the iron 56, and I'm asking over all supernovae where iron 56 has been seen, what's the distribution of energies? The total, by energy I mean total luminosity.
I'm not sure I understand the
I
question.
think maybe you just don't know. Ashley, do you know the answer?
You mean the masses?
Yeah, basically it's mass, but since we don't necessarily know the mass, if we have, obviously we'll have a redshift of some sort and measured flux, so we have a luminosity that is due to nickel 56, and I'm just wondering how constant that value is over supernovae.
Over all different
Yeah,
supernovae.
well, overall type 2 supernovae that have been looked at, which is a huge number, of course. But
It's less than order of magnitude.
less than an order of magnitude, okay.
Factor
I
of
mean, it's still, you know, if it's half an order of magnitude, that's factors of 3 or so. Would that affect your conclusions?
No.
Because you're, okay, well, very nice talk.
Thank you.
I'm just trying to understand exactly how
Great.
your conclusions
Clearly
are
intrigued.
based.
Thank you. And you got us back on track. So thank you very much. Crow, welcome.
My name is Segev. I am a junior studying astro and applied physics, interested in early universe cosmology and instrumentation. And for Astro98, I worked on GReX, the Galactic Radio Explorer, with Liam Connor, and it will be monitoring for the brightest bursts across the radio sky. So for a bit of context on fast radio bursts, the field started in 2007 with Lormer et al., who were combing through the Parkes archival data of the radio telescope in Australia and found this kind of waterfall pattern of a radio burst. It's of enough magnitude that it's putting off the same energy the sun would in 80 years in 1 microsecond. And so for a little bit, people questioned because of that if it was even real. And then they found 6 more in the Parkes archival data, 1 in Arecibo, and then they had a live detection. And then some were found to be repeating. And then the emerging question became, what is it? What's causing it? And there were a lot of theories, ranging from the magnetic hair of neutron stars as they became black holes, planets, light sails. Basically, people didn't know. And then in 2020, the STAR 2 collaboration released that it had found another FRB and had also been able to localize it. And it was right on top of a known magnetar. They also were able to get follow-up X-ray emission, and so it's now thought that FRBs, at least a large part of the population, is coming from magnetars. And we also now know that there are magnetars within our galactic plane, because that's where this one was localized to, which brings me to GReX. So GReX is a all-sky radio monitor. That's why the dish is slightly different shaped than what you typically see for a radio dish. It's designed to be looking at as much of the sky as possible at one time. And then in its box, one of the key features is these low noise amplifiers, cutting edge technology from DSA 110, which allows for really high resolution data, around 10 microseconds, which would allow us to study the broadband emission of these undiscovered galactic magnetars. And this is also hugely significant because these magnetars, we don't know a lot about the processes actually going on, so that broadband emission can tell us more about that. That broadband emission also can tell us about the intergalactic medium it's traveling at us through. And also there have been magnetars from over 13 billion light years away. And so it can also tell us about the early universe. GReX operates at 1.3 to 1.5 gigahertz band. You can see it at the top. And you can also see it overlapping with a lot of the observatories, which found FRBs in that band. And so this is adding the Harvard station. The goal is to have a network of these stations across the world, having 4 pi steradian coverage of the sky, also 24/7. And so these are the stations either currently up or going up. And off of that, we can model the magnetar fraction that we have coverage of. On the left is in terms of hour angle. On the right is in terms of hour of the day. And you can see from Harvard, which is in purple, that adding this station gives us a little bit more in hour, around 15 to 20, and also slightly at the very edge of the hour angle. And so then for GReX hardware, the important components are the Raspberry Pi, which turns on and off the snap. It's essentially the computer on board, but its main purpose is just for the snap. The snap is essentially programmable digital logic. It was developed for radio telescopes by Caltech, and then further customized for GReX. The FEM, shown top center, is the front-end module, and that is what's actively looking through the signal. It is also kind of filtering and then also amplifying with those low-noise amplifiers. So then a lot of what I did was software setup and tests. So for software, on the left, you can see inserting the card, which was put in, which is boxed in green. I also set up the operating system of the Pi. And a lot of the project was just kind of connections and making sure that the packets were traveling and getting through and looking through protocols. And so this is Wireshark, which is a software that allows you to look at the IP packets that are going through. And so then also we were initially looking for locations to set up GReX here. And we need to be above basically tree line and try and be as high above other interference signals that are being sent out along radio channels just from the area. So we want a tall building. Smith does not allow for installation. And there are two telescope domes on top of the Science Center, which would get in the way of that. So we did tests at the CFA here and also at the Science and Engineering Complex. And as you can see from the center, there were larger spikes for the cell towers and also for the hospital communications, which are just on either side of our band, that were kind of very much causing it to be noisy at the SEC. So it was installed here. Yes.
What period of time does that represent? Like how long did you look for that?
It's averaged for 2 minutes.
Average of
Yeah, that's for these plots specifically. Some of the other ones are longer and shorter, but yeah. And then we also did, once we had that, we had decided to set up here, we did system temperature tests. And so the way that works is we know the sky's CMB cyclotron radiation temperature. And then we take one of just the dish pointing up at the sky and then do one with foam that has been doused in liquid nitrogen and then can block the signal that would otherwise be coming in through here. And then from that difference between those two signals, we get power, which we can subtract due to the log scale to get what's known as the Y factor. And then from that, given that we know the temperature of liquid nitrogen sponge and also we know the temperature of the sky, we get our system temperature. So averaged across frequency, it's around 60 Kelvin, but also it's non-constant across frequency. So the center 1.3 to 1.5, which is our operating band, is where it actually dips the lowest, which is good. And then the GReX pipeline, this is what's constantly monitoring the signal we're getting, looking for FRBs. Because it's going through so much data, we can't actually save it. And so T0 is what's actually going, OK, this might be something. So it's the raw data that's voltage, and it's just been dumped into the server. And then T1 is it cleaned a little bit. So this is trying to get rid of some of the noise. And then this is also doing bandpass filters to try and get the edges off. And then T2 is trying to account for that RFI. And that is done by normalizing. And then T3 is where you get what you can recognize from papers as our science output. So that's the spectral data and our emission.
Can you explain why the RFI has that shape?
The water, yeah, that's because of dispersion. So essentially, it's traveling at us through the medium, and the longer wavelengths have less energy, so they're kind of getting caught behind and slowed down. And so that's why they arrive later. And so you can see that kind of waterfall pattern across frequency. Does that make sense?
It's not what it's asking, but keep going.
OK. And so then this is kind of GReX operational and on Sky working. And so the Grafana dashboard is how we monitor just that it's on Sky. And so it tells us kind of the CPU being used of the various components to the signal-to-noise ratio of the galactic, the galaxy. And so then on the left is a candidate injection. So what we can do is over just kind of the noise that we're constantly getting in, inject what we know to be the pattern of an FRB and check that the pipeline works by having it go, here, this was an FRB. And so this is then sent to Slack channel with people to review it. And then this is the future of GReX. So waiting, this is modeling its detection rate. And by that, hopefully within 3 years, we should be able to see an FRB. We're thinking of moving it to Oak Ridge Observatory, which is more radio quiet. So it would be able to do better in. And then continuing to add stations, particularly in India and the southern hemisphere, which would allow for more of that 4 pi steradians 24/7 coverage. And I'm originally from Alabama, so the idea is it's as far south, minus the southern hemisphere, as you can go without getting wet here. And so it's that if we add a terminal that I'd set up in Alabama, you can see the modeling. It gives us more than OVRO does at the edge of the hour angle and center of the hours of the day. And that raises our magnetar fraction from 0.8 to 1.2. I'd like to thank my PI. I had a lot of help from people in GReX Cornell, one of the grad students, Sasha, all the GReX people who helped, my AY98 professors. Yeah, PI was also very helpful. And then people helped carry. And then references, any questions?
So, questions?
Yeah.
Nash?
So I noticed there are 2 antennas in your field.
Yeah.
And presumably that's for polarization.
Yeah.
So could you comment on that?
Yes. So the actual path that it takes for signal has horizontally and vertically polarized, which are what you noticed inside the feed, and also on the outside, it travels to the box through two different cords, and so that horizontally and vertically polarized signals, by doing that and then later combining it, is how we get those characteristics of FRBs and are able to.
So I was actually also wondering if the FRB signal is polarized.
I imagine if the magnetar is rotating, it would be, but I'm not actually sure.
Highly polarized?
Yeah. Okay. And also whether the polarization measurement will help you, rule out RFI kind of signals. RFI signals will definitely.
It could, but also part of the design of GReX itself is, so there's also a station set up at Cornell, and part of what the pipeline does on the back end is it's designed to kind of cross-correlate. And so there's RFI here, and there's going to be RFI at Cornell, but the likelihood of the same RFI signal going off at both locations at the exact same time is so low that if both terminals get a FRB-like candidate at the exact same time and the signals match, we'd be able to assume that's an actual FRB. Yeah, there have been a lot of worries and mitigation of RFI because historically there's been people once detected an FRB and later found out it was a microwave going off inside the observatory.
How continuous is your coverage at this point?
At this point is
In both time and sky coverage?
so that was the plots from modeling at the very beginning. And so the right one is in terms of hour coverage, and the left one in terms of hour angle. I think either Australia or Ireland is in the process of going up, but very shortly going to be, so we're counting it. And so you can see that we have a dip around like 5 to 10 UTC, which we'd like more coverage at. And also that with what Australia is providing, we have more coverage, kind of later hour angles, but we do have some coverage across the entire band.
I'm asking because magnetars are detectable in gamma rays, and some gamma ray bursts just collectively are due to magnetars. There was one recently, for those who follow the GCNs, that was detected by Fermi from KES 73. And so if you were on the air then, so to speak, it would be very interesting to see whether you saw something as an exact time of that burst.
A lot of even the very first alive FRB, they did follow-up observations because they were convinced there should be X-ray emission. And the initial ones were not within the galactic plane, so they didn't find, they did those follow-up observations and didn't find any. And then for the galactic one, they did find X-ray emission. So the hope of GReX being able to find ones closer to us is that we'd be able to do the follow-up observations as soon as GReX detects something and see more of those characteristics and how it's doing in other parts of the spectrum.
Do you have a question?
Yeah, I have a quick question. Thanks for interesting topic. So, do you have to build any part of this device? And second question is, in an actual survey, how many devices do you need this kind of thing? Or just one?
And are they actually cake pans?
Well, it's called a cake pan dish. I didn't build the box itself. The idea is that it's supposed to be able to ship across the world, and then you just have to set it up. Majority of it is off-shelf components, except for the snap, which is done custom by the project engineer for GReX. And so I was mainly doing all the connections, the dish to the box, also doing server setup, connections to the server, We did have to kind of go in there in terms of that the Raspberry Pi's image had been corrupted, so we had to reload its operating system and a lot of the original GReX files.
I think you're selling yourself short. When it arrived, nothing worked. Like, yeah, every little piece of electronics was built, but we couldn't just plug it in. Larom had to debug every part of that, basically.
Is the plan for them to be able to work better in the future?
Yeah.
And how much does each one of these cost?
Like,
20K?
yeah, I was like, what am I allowed to say? And then,
Free labor.
so that was in terms of setup. I was doing a lot of the connections and also digging in on some of that. All the tests which have to be done at each station. And then what was the second question, sorry?
How many devices do you need in actual survey? How many this kind of device do you need in actual survey?
If they were all optimally placed, I think you only, I remember it being like either 20 something or 30, but keep in mind some of these have been set up, like Harvard is set up here because my PI is here and I'm here. It slightly overlaps with Cornell, so that's why we're looking at moving it now that it's set up. And so based off of that, it might be slightly more based off placement. Also that right now we have 8 already that can be ready to set up anywhere. And these that are on stack.
Thank you. Very impressively small scale experiment nowadays.
That's great.
If you put
Thanks, Larom.
My name is Joe Bradley. I'm a senior studying astrophysics and music. So unsurprisingly, my project is working on the development of a data sonification tool for glue. So data sonification is basically any sort of representation of quantitative data using sound, hopefully illuminating some of the trends in the data by ear. And obviously there's something inherently like musical about so much of what I learned about astrophysics. We're always dealing with spectral phenomena, we're dealing with wave phenomena. That to me as a musician always strikes a very musical chord. So it feels very natural to apply that. Thank you. That was off the cuff. So that to me always really spoke to the musical part of my expertise. And this is something that scientists have been doing for a little while. Ever since the early 90s, we've seen this interest in applying sound-based data kind of representation to these large data sets in hoping that kind of the more inefficient sense of sound and hearing that we have compared to our sense of sight can help illuminate some of the trends that are in the data that are difficult to see visually through data visualizations that are typically done. So just to illuminate a trend, we can see that the mentions of sonification in NASA ADS have basically been increasing exponentially since the early 90s. But it's been a relatively decentralized process. There are a lot of different packages that basically represent astrophysical data in a lot of different ways. This is one of my favorites that we discovered. It will be the most pretty sounding sonification you will hear today. But this is basically a sonification of Cassiopeia A using NASA data. I don't know if you can do this. Very nice. And as you can tell, the sounds that we're hearing are orchestral sounds. They are not sounds made directly from the data. Basically, when this circle from the center is expanding outwards, it's being triggered by the different bands of wavelengths in the light from Cassiopeia A, and that's triggering some sort of orchestral sound. And that, to the musical side of me, makes me very happy, and it's a very pretty sound. But to the more astrophysical science part of my brain, it makes me feel as though there's a lot of fidelity in the data that's being lost here. We're adding in overtones through trumpet sounds and violin sounds that are not really there in any of the data. And so I wanted to kind of make it a challenge to myself to try to represent data in a little bit more of a high fidelity way when it comes to the sound, where we can kind of actually make it so that everything in the sound indicates something astrophysically about the data set. So that was inspiring to me, but I wanted to sort of take that a step further, or a step backwards in terms of sound quality. But, and then speaking of trends, one paper that was very motivational for me to start this project was written in part by my advisor, Dr. Arcand, And this paper basically acknowledges this increase in sonification that's been going on, especially even by NASA, but acknowledges that the process is inherently decentralized, and then introduces this very important topic that became very titular in my project, which was increasing the accessibility to people to basically like blind or low vision scientists, BLV scientists, that cannot consume data visually in the same way that most of us do. So that became a very important part of the underpinning of my project, is increasing that accessibility. So to that point, why sonify? What's the point? Is it gimmicky? Is there something really scientifically significant that we can draw from sonification? The first thing, as pointed out in that paper, is the issue of accessibility. Astronomy, of course, prioritizes visuals. It's a very light-based field, and so it makes a lot of sense to represent a lot of our data visually. And that fundamentally creates a barrier for people who are BLV scientists. And then separately from that, and a part that I found very interesting, can we, through sound, add to novel discovery and analysis of data? As I mentioned before, our sense of hearing is a lot less efficient than our sense of sight. You know, it's a lot less well-trained for most people. So when you hear something, you're forced to kind of hear every little bit of it. You can't like scan over data in the same way that you do visually. And so can that lead to discoveries that are new and are not as obvious through typical visualizations? So with that in mind, this automatically triggered to me, I need to deal with a couple different types of data when I'm dealing with sonifications. One of which is intensity time series data. Of course, we see this all the time. Things like transits, things like bursts. I wanted to sort of, the most obvious, like as a musician and a music producer, I know that the musical parameter that we are most sensitive to is like chroma, like the pitch, basically, the height of the pitch. So it seemed very obvious for me to find a way to represent basically intensity through pitch data. And then the other type of data, little FRB sneak peek here, is spectral data, of course. And to me, again, as a music producer and sound designer, seeing astrophysical data represented this way always struck a musical chord, again. And I see data in music represented like this all the time, with frequency on one axis and time on the other, and seeing how different sounds represent themselves visually through spectra like this. So that, to me, automatically made me think music, and I want to incorporate these two types of data into my sonification. And so I sought out to look for some projects that could use sonification that would basically incorporate both these types of data. And that is when I was introduced to the Pulsar Science Collaboratory. This is basically a project that trains high school students and teachers to identify pulsars from pulsar candidates that are identified using software. Some of them are very good, like this one, and some of them are very bad. And essentially, high school students and teachers are trained to look at these four graphs. One, which is intensity versus time for two phases. Anything that shows like two of the same phenomenon, that's the same thing just twice, so that it's easier to look at and you can see the pattern a little bit better. But that's intensity versus phase, time versus phase to see if the pulses are on a consistent basis. Then we have a spectrum with frequency versus phase, and then a dispersion measure, that's sort of the reduced chi-squared, for the confidence measure on the different dispersion measures that are the model being mapped onto the pulsar. So these are the four graphs that are shown to participants, and from this, they have to determine whether or not this is a good pulsar candidate. Now, Maura McLaughlin, who I spoke to from West Virginia University, who works on this project, wanted to make this project more accessible for BLV individuals. So she was looking to basically make a way to determine from these four graphs whether something is a pulsar without having to look at the four graphs. So that was my first project. And the second one, very convenient that I'm going after Larom. We had a presentation from Liam Connor at the beginning of the semester, and from that, it really, again, it made me think of music and made me think of sound because of the way that FRBs distribute this consistent dispersion measure, and how basically scientists are already calling it the sad trombone sound, like starting at a higher pitch and then slowly moving downwards in pitch across the light frequency spectrum. And I wanted to make a way of visualizing this through sound. And then, of course, glue product placement. Here's glue. Because so much of the literature explains how sonifications are particularly useful alongside typical data visualizations, it seemed very obvious to add this capability to the glue software. And so it was a great candidate for a way to implement something into a little bit more of a practical way, and kind of have a place to siphon my code into once I had it working outside of software. So to begin, The Astronify package is something that I was introduced to very early on, and its typical functionality does that very kind of height is higher pitch kind of sonification, and so this was an obvious choice to go with when it came to sonifying the first and last graphs, where we want to see two sharp peaks and then a clear peak in the reduced chi-squared at a particular dispersion measure. And then upon the recommendation of Maura McLaughlin from WVU, for these two spectra in the middle, we want to see two dark lines. That's what we're looking for a good pulsar candidate. So basically she said, what you should do is find where those two dark spectral lines are and sonify along those lines, basically along the y-axis on those two dark lines, in a way that shows that the dark line in the first graph that is spectral shows that it's pulsing at a consistent rate. And the second one is that basically pulsars should be broadband. They should have high flux basically across the frequency spectrum, so we want to see a consistent dark band. So my goal was to sonify these two, basically height versus time is pitch. The ones in the middle, I wanted to find a creative way of using my own code and not a package of sonifying along those lines to show that there is two dark bands. So the way that I did that for this type of graph is basically you grab the data from the database, you basically just concatenate it twice so that it represents itself in the same way as the graphs do, and then using Astronify, turn that into a Sona series object, which is part of the documentation, sonify that, and then write the audio file. So relatively simple, and that should give us a pretty easy, high intensity is high pitch, low intensity is low pitch, and you can hear two pretty clear pulses. And then for the dark bands, my code finds the darkest column, basically stores the intensity values along whatever the darkest column is, eliminates values below a certain threshold, because you really below in pretty much every representation that I saw, the dark lines are much above the average of the noise across the rest of the spectrum. So I eliminate values below a certain threshold, basically multiply that by a sine tone so that the intensity controls the volume of the sine tone, and then write an audio file based on that information. So sonification time. This is an example of a great pulsar, very high chi-squared, and a terrible, terrible pulsar, very low chi-squared, which is just clearly noise. But these are the types of things that we're distinguishing. You can take a moment and kind of tell yourself that you could figure out which one is a pulsar visually, and then we can do it with sound. So as you can see, no dark bands in the middle, clearly not a significant spike. You can see why maybe the software grabbed it, because there's something kind of spiky about the noise at that moment. And then you can see that the peak in the chi-squared is heavily localized compared to the much better looking pulsar. So this is clearly, you can also see that from the noise around in the dispersion measure plot, which we can hear from the sonifications. So let me play, hopefully this works. Here is basically the two pulses from the good pulsar. So not as beautiful sounding as the one I showed you earlier, but you can hear that there's two pretty sharp increases in pitch, and then let's compare that to the bad pulsar candidate. So you can see that the difference in pitch is heavily reduced. So you can see that from the first graph. And then let's listen to, so this one is a little bit longer. Again, it's just a sine tone with the intensity mapped onto the volume of the sine tone across what it located was the dark column above. So you can hear that there is sound along that whole dark column. Compare that to when it tries to find a dark column amid all the noise in the one right below it, and doesn't do a very good job, and you can hear how inconsistently the sine tone represents itself. So it's just basically finding a few moments of darkness among the noise and sonifying them. But if you listen to those two back to back, you can hear clearly that in the top one, it represents itself much better. Here is the spectral data on the top. And here So clearly much less consistent. And then for the dispersion measure plot, here's the top one. So you can hear from that it clearly has a peak, but it's also quite clean. And that is one of the what I love about the Astronomy package is that since it adds a bunch of subharmonics and overharmonics, basically you can hear very clearly that this is a much noisier dispersion measure plot. You can hear kind of the wobbliness. So if you were trained to listen for that wobbliness in this plot, and I tried this multiple times with various different pulsars, some of which with a little bit more like kind of in between chi-squared values, it's pretty easy to tell which ones are good pulsar candidates and which ones are not. So this code is ready to be implemented into the Pulsar Search Collaboratory. And then I went on to try to sonify spectral data. This was a test pulse, which was given to me by Liam Connor. Again, as Larom was talking about, this test pulse is fed into the system to see if the system is properly identifying FRB-like phenomenon in the sky. So for this, it was a little more complicated, and I was also doing it from scratch because I wanted to represent as much of the data with high fidelity as possible. So basically, you map all of the light frequencies to a sound frequency, multiply a sine wave at that frequency by the intensity profile, basically along the time axis, and then add that to an overall waveform. So basically, from that, you get spectral data represented, and you're basically reverse engineering a Fourier transform of the sound, of the what's in light space to sound space. And what's nice about that is that you can really customize how you're compressing the data and how the data is representing itself. So you can really decide how much nuance you want to add in. This is an uncompressed version where basically I did not weed out nearly as much of the noise. So you can hear that represent itself in a way that you ignore the noise very easily visually, but some of the more nuanced frequencies that are representing themselves can be heard much more easily through the sonification. So as you can hear that decrease in pitch. I'll play it again. Try to play it again. Oh, okay. So I also went ahead and compressed the data a little bit in a different way, basically weeding out all of the noise, and you get this sound. So that's what that sounds like. You can hear much more clearly that the very particular sweep is kind of being pushed much more through the noise in that way. But this was very illuminating to me because it showed me how, as two equal representations of the same visualization, when you're representing it through sound, because our sense is so much less efficient, you hear all of the little noisy phenomenon in the data. And that to me said that it could be very useful to, in the future, try to use sonifications to weed out good FRB data from RFIs, because you get this sort of level of high fidelity hearing all the little nuances that are going on in the signal that you don't quite pick up on when you're looking at a graph of the same signal. So I went ahead and met with John Carriffio, who's a genius, who works on the GLUE back-end software, and tried to come up with kind of a skeleton for how I would implement this code into GLUE. I am not a software engineer, so it got very complicated very quickly for me, but I was able to basically come up with a good representation of what this would look like. You would load in the data very typically into GLUE, as you can see at the top. GLUE obviously can interpret lots of different data types and files. The sonification tool is right here. I picked the little rainbow symbol because it kind of looks like headphones. So that appears right up there in the toolbar. If you click that, it prompts a user dialog, which kind of lets you pick the different parameters of your sonification. And then after that, it prompts you to name your file and store it wherever you'd like. It kind of felt like magic to be able to do my own things in this code and have it show up. It was very cool. And there's still work to be done with implementing this into the back end of GLUE so that it works with all of the GLUE capabilities. But that it was very cool to see how the skeleton of that would work and how you would load in data and sonify it. So obviously from this we can see that hopefully this code can drastically increase the accessibility of the Pulsar Science Collaboratory so that more people can participate in it. And I think what I've done is quite good at weeding out bad pulsar candidates in much the same way that visualizations do. And And then also, this really showed me a lot of interesting ways that sonification can be helpful with spectral data, with really like hearing some of the nuances that show up that you kind of decide to just gloss over when it comes to visualizations of the data. And then, working this into glue, so much of the literature explains how useful it is to work with it alongside data visualizations that are more typical. And glue is incredible at creating different ways to look at data and to interpret different data sets in very complicated ways that work well with each other. So I think that implementing this alongside the typical functionalities of glue would make it very useful. So obviously, future steps, finish implementation into the real PSC. Obviously, keep sonifying things spectrally and try to figure out what it's good at weeding out, especially when it comes to looking at RFIs versus FRBs. And then finally, finish the implementation into glue so that it can function alongside all the other wonderful glue functionalities. Okay, thank you very much. Obviously, special thanks to Kim Arkan, my advisor, Alyssa Goodman, Liam Connor for being very helpful and for being my reader, Maura McLaughlin for helping me implement this into her project, and a huge thanks to John Carifio for doing things that I could literally never do on my own. And then thank you to the whole cohort. You guys are very fun and fun to be around. So thank you all very much. And I'll take questions. I know I went a little bit over.
We have time for 1 or 2 questions and then a break. We can keep talking and playing during the break. Questions? Liam?
So in the pulsar plots where you have time and frequency versus pulse phase,
Yes.
I'm a little surprised at the choice to just select the phase bin where you have signal. I mean, visually, the thing that pops out is the signal on top of the off pulse phase bins, right?
Right.
Noise.
Uh-huh.
So could you think of ways to incorporate that in the sonification, kind of like what you did with the FRB?
Yeah, I was thinking about that. It was mostly on the recommendation of Maura McLaughlin to just try to sonify along that band. I was thinking that possibly a little bit more of an accurate way that would take more of the information that we see visually and sonify it is instead of picking like one band, like pick the highest bin of maybe like 3 pixel bands or something and then sonify along that. And maybe that could incorporate a little bit more of the nuances that we see visually. Like, I think that she was afraid of incorporating too much of the spectrum of data because then the sound would like inherently get more complicated. And if we could do something that was relatively simple, that was a pretty simple sound, then like ultimately that might make it easier to be able to go through the data quickly and weed out the ones that are quite good and the ones that are quite bad. But I agree that taking some of the nuances that we can see visually don't.
One thing I found, to go to what Liam was saying during the whole presentation is, and by the way, thank you for all the glue plugging. I had no idea, by the way, not me. But anyway, so but in what you're saying about combining the visualization and the sonification, you could do that even for someone who couldn't see,
Right.
by essentially putting the cursor where the dark band is, and then saying, use the 4 keys that people are trained to use if they can't see. It's something, this one is up, this one is down, this one is sideways. This is, return is reset or something like that. And you're telling them you're putting it on the dark band,
Yeah.
and then you let them go up, down, sideways, and the sound matches with what
Right.
they're doing. I think
Yeah.
that would be really great.
Exactly.
Yeah, and we can do that. John will do
Yeah,
it
we'll
next
do
week.
it. Yeah.
Anyway,
You can finish it in
Dinesh,
5
why
minutes.
don't you take the last question?
Most radio astronomical signal is obviously noise.
Yeah.
So if you listen to
There's a
it, it's his kind of sound.
Yeah.
So I was really curious why in any of your sound examples that you have played, there is no noise. It seems you're basically using a tone generator or like sine wave generator or some combinations thereof. But why not also use a noise generator?
So you're saying
So-
noise in the background?
Yeah, in the background. So for instance, in a case where, look at one of these lower plots where the signal is very, very weak and noise is dominant. And in such a case, you will hear the white noise kind of thing.
Right.
And, I was just curious about that. And the other sort of related, very quick comment is the ability of the human ear to pick out a tone in the presence of noise, if there is one. So that could be potentially very interesting and useful as well.
Yeah, no, absolutely. I mean, for particularly like dealing with the noise, like you're right, like in some of the instances where I was sonifying, like I made it a priority of mine, like sound design wise in the code and outside of the code, to take out some of the noise so that we could hear the sound a little bit better. And that's something that we can definitely do with all of the various music technology that we have. And yes, to your second point, like I think that one of the main things that I discovered in doing research about sonification was that we kind of exhibit a very like conservative bias when we're looking at visualizations, where it's like when you see a signal, like you are like more hesitant to be like, oh, that's a signal, I'm looking at that, I can see it among the noise, and I can, but when we exhibit a liberal bias when we're listening to things, because our ears are quite sensitive to signal above noise, because that's what all of listening is, basically. So using them together is kind of like, you can kind of balance that conservative bias of looking at data visually and the liberal bias of listening to data and over-reporting sounds that you hear. And so for those of us that have both senses, it's easy to kind of check one with the other. So yeah, no, I agree. I think that the ability of the human ear inherently to pick out signals above noise makes sonification, and particularly astronomy, very useful.
I'm going to say one last thing, and then I'm going to cut this off so we can have some nice hot chocolate. Thank you, Peg. Which is that in the visualization, you see how there's like the grayscale noise thing there, right? We all know that people play with the levels to make that look different, right? And what's so interesting about what Joe has done in the whole conversations with Kim is that, yes, typically people want to make it sound like an orchestra or want to make it sound like a pure tone. It's kind of the same way people want to clean up bad images. And I don't think there's been that much work in sonification to kind of mess around with what it looks like the way there has been in visualizations. That's a whole new field. You can see from just these 3 talks that there's like a huge range of things that the students have worked on. And so thank you already. This has been great. And we'll take a break, and then we will come back at whatever it says on the schedule. I can't remember. For 3 more talks, and then there'll be another break. And so
Thank you so much.
Okay, let's start. So good afternoon, everyone. Thank you so much for coming by and listening to our presentations. My name is Jasmine, and I'm a junior at the college studying astrophysics and physics. Today I'll be presenting our research on turbulent mechanisms of cosmic ray reacceleration in galaxy clusters, insights into the universe's largest particle accelerators. So let's dive in. So as a roadmap, this research essentially focuses on characterizing turbulent motions within galaxy clusters using 2 different methods to isolate rotational and divergent components. Additionally, we present a cosmic ray reacceleration model that accounts for rotational turbulent motions. Our main aim is to understand how turbulence contributes to the reacceleration of cosmic ray electrons and sustaining diffuse radio emission, which we'll dive into now. So galaxy clusters are gravitationally bound structures containing hundreds to thousands of galaxies, hot plasma, and dark matter. Essentially, these function as cosmic laboratories for studying high-energy astrophysical processes. So the ICM itself is the hot magnetized plasma that fills in the space between galaxies within a cluster. So comprised primarily of ionized hydrogen and helium. The ICM reaches temperatures of 10 to the 7 to 10 to the 8 Kelvin, which causes it to emit X-ray, which we're able to capture in our telescopes. The ICM is additionally a magnetized reservoir of relativistic particles, and which includes cosmic ray populations. This research is concerned with cosmic ray electrons embedded in the ICM that interact with magnetic fields, specifically those that are reaccelerated by turbulence. So why do we even care about this? So radio observations reveal diffuse radio emission regions originating potentially from relativistic electrons and magnetic fields within these clusters, often as a result of mergers. So for example, here we have an image of Abell 2744, which is in the process of depicting 2 galaxy clusters merging. So up on the left, we have radio relics, which are elongated arc-like regions typically located in the outskirts, often aligned with shock fronts. This is essentially where the kinetic energy of infalling material is converted into heat and particle acceleration. But we also have radio halos, which is a bit more pronounced, and they're centrally located, which more larger scale regions that permeate the cores of galaxy clusters. So in this research project specifically, we focus on radio halos because they provide a direct link between turbulence in the ICM and the reaccelerations of cosmic rays over large spatial scales. Unlike radio halos, which are more localized, at shock fronts. The radio halos permeate the center, and so they help us understand how turbulent motions themselves transfer energy to relativistic particles over the large-scale radio emissions that we're interested in. These emissions are produced through something called synchrotron radiation, where relativistic electrons spiral around through the magnetic field lines, releasing energy as radio. So this brings us to our key motivating question. So why do we observe diffuse synchrotron radio halos on scales far exceeding the typical diffusion length of the typical electron? So your typical synchrotron emitting electron has a diffusion length of approximately 10 parsecs. However, radio observations exhibit diffuse emission across megaparsec scales. Here's a visualization plotted in a logarithmic scale, and you can see that there is a very stark difference between the two scales that we observe. So this necessitates reacceleration mechanisms or some type of other process that produces or energizes electrons locally to compensate for the significant energy losses these particles experience within their typical diffusion length. And so such mechanisms need to provide sufficient energy gains to sustain the observed synchrotron radio emission that we observe, bridging the gap between the microscopic processes governing the particle diffusion and the macroscopic features of radio halos. So now let us consider turbulence that emerges as a result of a galaxy cluster merger. So during a merger, the immense kinetic energy released by colliding substructures is injected into the intercluster medium at large scales, creating bulk motions and larger eddies. Through the process of energy cascade, the kinetic energy is transferred to progressively smaller eddies where they break down, as you can see in this diagram. At these smaller scales, the turbulent energy is either dissipated as heat or used for the reacceleration processes that we are interested in. So we can consider two different types of cosmic ray reacceleration mechanisms. First, we have transit time damping, which essentially is a process where we have cosmic ray particles interact resonantly with turbulent magnetic compressions, which allows them to gain energy. This mechanism relies on a coupling between the particle's actual motion and the parallel magnetic field oscillations, which makes it effective, especially in regions where there's compressive turbulence. But there's also super alphenic solenoidal turbulence, which is the focus of this research. It refers to turbulence in a plasma where the turbulent velocities exceed the Alfvén speed, which is essentially a regime in which the magnetic field becomes relatively weak to the turbulent kinetic energy. So we are interested in particular in the rotational turbulence as a cosmic ray reacceleration mechanism because it effectively channels turbulent kinetic energy into the stochastic acceleration of ray electrons without dissipating it into compressive heating or shock-driven processes, for example. So to simulate the dynamics, let me see if I can get the video on. There it is. There we go. We use, oh, that was really quick. But that's a much speed run version. I guess it's just technical difficulty. But so to simulate the complex dynamics of the ICM, we use a repo, which is a moving mesh code that solves magnetohydrodynamic equations on an unstructured moving Voronoi mesh. Voronoi mesh just means that you have like that very like structure and different cell sizes that interact like that. And so a repo combines the advantages of both grid-based and particle-based methods, allowing for more accurate modeling of fluid flows with reduced numerical diffusion, which is very important for getting high resolution for the things that we want to look at. So for simulations, the source of cosmic rays are from AGN, active galactic nuclei, which refers to a compact, like highly energetic region at the center of galaxies that are powered by the accretion of matter onto supermassive black holes. So in this model, we essentially put cosmic rays where at the time, which you can see at the left, is essentially a snapshot of where these cosmic rays have already spread to really large radii. So our simulations show a really strong spatial correlation between the magnetic field strength and the cosmic ray energy density. Notice how there's like concentrated activity near the center, and then you extend filamentary structures outwards into the medium, which suggests a really direct connection between the morphology of magnetic field strength with the cosmic ray energy density. the actual extent of cosmic ray energy distribution in galaxy clusters, which already resembles the large-scale structure of a radio halo, is a result of mixing processes within the ICM. So mixing essentially refers to the redistribution of cosmic rays and magnetic fields by the turbulent motion. So turbulence has a dual purpose. First, it generates irregular fluctuations in the magnetic fields, which essentially influence the trajectories of the cosmic rays through mechanisms such as scattering, for example.
Just to be clear, these are both from peripheral simulations, right?
Yeah, this is our plots. Yeah. Secondfold, we have turbulence actively redistributes cosmic rays in the ICM. So not only are they transported along large spatial scales, but they're also exposed to regions where they have the potential to be reaccelerated. But to analyze the turbulent velocity further, from our simulations, we use Vortex P, which is a code that performs Helmholtz-Hodge decomposition. So essentially, you can take any sort of vector field for its velocity. Here, this is just a random velocity turbulent field. And you can separate it into both solenoidal and compressive components. Solenoidal is essentially dominated by curl, and compressive is dominated by divergence. So what Vortex P does is that it employs a multi-scale filtering technique to iteratively determine the appropriate filtering scale at each point so that we can accurately capture turbulent motions. So while the reaper provides outputs that include the full velocity field, these outputs inherently contain contributions from both turbulent and non-turbulent phenomena, such as shocks and bow flows. So to interpret the turbulent dynamics from a repo's outputs, we apply like a simple assumption that is based on the computed curl and divergence of the total velocity field at the specific resolution scale. So this manual decomposition allowed us to have a good approximation, but what Vortex P does is that by using Helmholtz-Hodge decomposition, it filters the velocity field and isolates a true solenoidal and compressive turbulent motions. So our analysis shows that for solenoidal components, both methods agree well for the most part, suggesting that solenoidal turbulence is reliably captured. Analyzing the solenoidal turbulent velocity, we found that the rotational motions, which are associated with flows that are effective at amplifying the magnetic field through small-scale dynamos, are really crucial in the reacceleration of cosmic ray electrons. And so by the fact that we have a more or less good agreement between those two, that reacceleration models that rely on solenoidal turbulence are more robust. And
Tell us again what these two plots that we're comparing on?
yes, so these are spatial projection maps. So this is essentially like you take a specific region of space. So here it's around like a 4 megaparsec radii. And what you're seeing here projected on is the velocity, both are solenoidal velocities. The one on the left is from a repo, and the one on the right is from Vortex P.
Vortex P is analyzing the retro simulation, right?
You can extract the velocity field, and essentially by getting that velocity information, we're basically just like projecting that onto like a spatial graph, if that makes sense. Okay. So however, significant discrepancies arise when we discuss the compressive component. That indicates that standard simulation outputs may not accurately resolve compressive turbulence without advanced filtering. So as you can see, the one on the left is a repo, and it seems much less physical than the Vortex P counterpart. Essentially, because Vortex P uses the Helmholtz-Hodge decomposition, it has a more accurate representation, whereas the compressive component can be amenable to numerical artifacts and may not be as well at filtering shocks. And so this suggests the need for more sophisticated methods for filtering when it comes to compressive turbulent velocity. So we can further quantify this by looking at histograms of the turbulent kinetic energy flux. So for the solenoidal component, you can see that based on the, when you plot the specific velocities for each different type of method, the solenoidal seems to be agreement for the most part, which is consistent with more or less similarity we saw from the projection plots. However, the histograms for the compressive components, you can see that the Aripo compressive velocity has a broader distribution and is systematically lower, which suggests that it has certain difficulties and can be susceptible to interpolation artifacts or other methodological biases. This essentially reinforces the robustness of solenoidal turbulence while highlighting the need for more advanced numerical methods to accurately characterize compressive modes. So lastly, we discuss the turbulent reacceleration timescales. So in these plots, we have the background color map, which is a projection of the cosmic ray pressure, essentially indicating like regions where we have cosmic ray pressure. And then the contours that are overlaid indicate regions where the reacceleration timescales are shorter than the actual cooling timescales for the electrons. So we have a free parameter called psi, and psi essentially is the mean free path of the particles relative to the turbulent scale. And it is a region where turbulent reacceleration dominates over cooling losses, making the process efficient. One key feature of these plots is a difference in the upper right corner. And so the vortex P method shows contours there where their CR pressure is effectively 0. So this discrepancy essentially arises, we think, is because vortex P focuses on the solenoidal component of turbulent velocity and without explicitly incorporating CR pressure into its calculation for this particular model. As a result, contours in CR-free regions reflect mathematically possible reacceleration conditions, but they lack physical relevance for that up there. Whereas like when you have, because vortex B employs the filtering length scale, it represents the turbulent eddy scale derived from the solenoidal velocity fields, which is a general property of turbulence and not directly tied to CR pressure. Whereas we derive that length scale from the cell volume for a repo, which is more of a physical measure of spatial region containing gas volume, which appears to do a little bit better in that respect. So looking ahead, future research should incorporate additional cosmic ray physics into simulations, so including things like cold fronts, filaments, and shocks in more detail for it would be really beneficial, and also the incorporation of secondary cosmic rays. So actually quantifying contributions from like hadronic interactions would be pretty interesting. And as we emphasized, compressive turbulent modes aren't really as well resolved. And so evaluating other reacceleration models such as transit time damping that relies on compressive turbulence would be very helpful. So for acknowledgements, I would like to give many thanks to Dr. Paula Dominguez-Fernandez, who's right over there, for her being a great instructive advisor and for all her help in making this project a reality, as well as Dr. Vadim Semenov, who also was a tremendous help, and our PI, Professor Lars Lundqvist. Also would like to thank the AY98 teaching team and Professor Charlie Conroy for agreeing to be the reader for this project, and of course, all of the AY98 cohort for trekking to the quad and for FOHO dinners. These are references. Okay, thank you. I'll take any questions now.
Thank you. So we have time for a couple questions. I have one question. I'm still not
I can go back to
understanding.
that, yeah.
Yeah, so you have these plots, and on the one side, you're saying that's the Arepo method, and on the other side, you're saying the vortex P method. There's only one simulation, right?
Right, but what happens is that vortex P is essentially a filtering mechanism. So you still technically, so the simulation is done with the repo, but you add an extra layer of filtering so that it employs the Helmholtz-Tarski composition, which is basically like you use more math that is much more attuned to the actual fluid dynamics, rather than just making the simple assumption of taking like the curl or the divergence of the velocity field from a repo itself. So basically you just like get two different data containers and then you just like project it onto like a spatial map. So this is essentially
You're
like...
essentially saying like that's the raw values and that's this filter with vortex P?
Yes, sort of. So it's the raw output with the added assumption that we calculated ourselves. Like it's not necessarily like vortex, Arepo doesn't like output directly like, oh, this is like your, this specific like solenoidal compressive velocity.
Right.
Like we have to manually do it with code and like calculate the curl and divergence and then calculate it ourselves. But vortex P in of itself is a separate filtering mechanism that is an alternative to our manual decomposition, if that makes sense.
So is it supposed to be just like the solenoidal component in these plots?
Yeah, this is just solenoidal.
On
and
both,
then
on the left also?
yeah, both of these are solenoidal. So you can see that they have like similar, like they look similar. It's just that consistently when we do these projection plots, the vortex P has a much more smoother distribution. Like on the left, you see that it's like much more starker contrast in values, and that we think is because vortex P seems to have that advanced filtering that it employs, is much better attuned at actually picking up the turbulent motions, whereas a repo can be contaminated by non-turbulent motions like shocks or other things. And that leads to sort of pollution of data, which would be bad when you're feeding it for like reacceleration models, because these reacceleration models are specifically use these different velocities to calculate the reacceleration timescales.
That's very helpful.
And so yeah, this is just like a spatial map across like a radii of like 4 megaparsecs in both directions.
Ashini.
Yeah, thanks for the interesting talk, Jasmine.
Yeah,
so
for sure.
what kind of elementary particles are involved in this simulation?
Oh, so yeah, our particles are cosmic ray electrons that are produced from like AGN.
So it's all electrons?
Yeah, all electrons.
Terrific. So in the interest of time, I'm just going to cut it off there and say, Bruna, come join us, please. Thanks again.
Hi everyone, my name is Bruna Biz. I am a junior at the college and I study astrophysics with a joint in physics, and my PI this semester was Alyssa Goodman. And we worked on, we were interested in ChatGPT being on the rise and this idea of generative images, and so we tried to apply that to astrophysics, and we tried to work with the question as to why these large language models can't generate informative astrophysical visuals and how we can fix that. And so our motivation for this project came from an image that was generated by ChatGPT, or DALL-E I should say, and it is this beautiful image that was prompted by the question, or I guess the statement of generate a map of the 3D structure of the ISM. And as you can see with this image, there are several things wrong with it, but the main one is that there's nothing related to the interstellar medium. And another one, the other one is that it took, I guess, like the word journey very literally and tried to map out some circular platform indicating that you are, actually taking on this journey in order to build the ISM. And then down here you can see that it does mention some things related to the ISM, such as SIBO, the Worldwide Telescope. The spelling is obviously not great, and so with this image, Alyssa was very interested how these models sort of work and why they are not accurate, and how we could potentially fix that. And our other motivations were these 4 points as well. And so the first was new infographic generation. And so there are, astrophysics is a field that kind of fuels off of these diagrams and graphs and infographics. And so a big thing would be that if DALL-E and these other LLMs were able to create infographics that were informative, they could potentially do so in a way that we have not thought so before as humans. And so they would be able to potentially model this information in a way that is even more informative than how we do so, and so it could change the way that we look at the field. It could also aid future research, of course. So if you are doing something as Jasmine did, instead of maybe wasting a lot of, not wasting, but spending a lot of time coding, you could potentially have a map like that generated. And then another thing would also be accessibility. And so as I will talk about later in this presentation, a potential thing that could help improve these models would be greater descriptions of the infographics and diagrams that exist within astrophysics. And with this increase in description, it could also help with accessibility. So as Joe stated, for scientists who are low vision or blind, these descriptions would be able to, I guess, mend that gap as well. And then it could also help lower the entrance barrier into astronomy. So astronomy is obviously a complicated field and takes a lot of hard work, of course, but it can also be very intimidating to join. And so as ChatGPT becomes more accessible to the general public, it is possible that as more people use it and are trying to learn on their own and research new things, having this ability to generate good and useful infographics could help people learn quicker and better, and inherently would lower this entrance barrier. And so the test case that we used to kind of focus on infographic generation with DALL-E and ChatGPT was the Hertzsprung-Russell diagram. And the reason as to why we chose this diagram is because it is a staple infographic in astronomy and something everyone in the field is familiar with. And it has a very simplistic structure. It is 2D. The main sequence is plotted along the main diagonal from the upper left corner to the bottom right. And the white dwarfs and supergiants are clearly labeled along with giants. And the axes are clearly labeled. And so it is something that you could look at and draw quickly with a pencil and paper, for example. And so we focused on the Hertzsprung-Russell diagram. But before getting into everything that we did, let's quickly explain the Hertzsprung-Russell diagram. And so this is let's say, a stellar nebula. After a stellar nebula, you would get the formation of stars. And so these are the main sequence stars. So you have the spectral types, their temperatures, their relative sizes. And from main sequence stars, you typically get either super red giants, which are these very large red stars that have accumulated a lot of mass due to the burning of their hydrogen into helium, and so then they expand. And then after they explode due to the collapsing of their cores, you either get a black hole or a neutron star, and then in the other case, you would get a regular red giant. And after a red giant also collapses, you would get a planetary nebula, and then after the planetary nebula usually results in a white dwarf, which will eventually become a black dwarf, but our universe is not old enough. And so what are diffusion models? Diffusion models are what these generative image models use in LLM contexts. And they are generative models that learn to create images by removing noise in iterative steps. So you can imagine that you have a canvas that is just gray noise. And the way that they work is that they predict the noise, and essentially over multiple tens to hundreds of steps, they go and remove the noise until they get to a refined image. And that is essentially how they train, is by predicting this noise. So then when they go to generate new images on new prompts, they have a sense of they have an idea of how to predict the noise that will come from the generated canvas based on a process that happens in latent space, which is this kind of abstracted space where language models kind of match images to texts, which I will talk more about. It can sound very confusing right now. And so this is a very simple image that kind of denotes how stable diffusion works. And so a text encoder, in this case, which is CLIP, which was created by OpenAI, and it stands for Contrastive Language Image Pre-training. And essentially what a text encoder is you give it a prompt, such as dog riding a horse. And it will take the words and vectorize them. So you can imagine that it'll take the word riding and split it into ride in ing, so the actual verb and then the tense. And then from there, it'll take all the vectorizations of the words and embed them in a abstracted space called latent space. And in this latent space, it is able to match the vectors to images that it was already trained on. So it would take dog, and it would maybe find images of dogs so that have the same shared vector, and then be able to match like your prompt to images that it has already known, that it already knows. And then the creator, so what is a UNet and a scheduler, is this denoising step. So after going through this latent space, it is able to like abstract the things that you told it. And then instead of actually generating the image from that, it just creates a noisy canvas. And then in the UNet, it goes denoising this, and then the decoder is what will produce the final image. And so yes, this is a kind of image that describes how the training process works. So for example, this is a training image of Kyoto, and you have some noise over it, and so the UNet is able to predict the noise with that first gray canvas, and this is the actual noise, and then it'll learn through backpropagation and other machine learning methods, and eventually it gets good at this, and that is how you get DALL-E. And so the methods that we used in our research to kind of try and understand why astronomical infographics were not being produced at a good quality, was by having ChatGPT and DALL-E generate HR diagrams from simple prompts such as generate an HR diagram. And then from there, we decided to feed objectively good Hertzsprung-Russell diagrams to ChatGPT, and then have it describe these diagrams and generate the infographics based on its descriptions, because we figured that if it is able to thoroughly describe an image, it would be able to match this description to an image that is of higher quality. And then after that step, we said, okay, if it is not able to accomplish the second step, which we will see that it was not, we will try to see if it can generate simple Python code that is able to use like matplotlib and plot a simple HR diagram on a graph and go from there. And so with the first method, very simple prompts, we got these beautiful images that you almost want to hang on a wall, but make no sense. They have nothing to do, well, I don't want to say nothing to do with an HR diagram, but as you can see, they're not comprehensible. The spelling is very convoluted in many of these, and it does make an attempt to, use the color scale that we're accustomed to in an HR diagram, but there's no proper mapping of like the color scale in relation to stars and temperature. And these diagrams, we also noticed that they follow a very circular pattern for some reason. Well, in that case, I was very surprised that we were able to get a 2D diagram. That was the only, I think, iteration where we were able to get a 2D image output from DALL-E when prompted to create an HR diagram. And then following the second method, we used these two images. Well, we used more than, but these two are good examples of HR diagrams that we fed to ChatGPT and had it describe them thoroughly. So not just what an HR diagram is, but also the physical aspects. So how does the axis work and the color scales and things like that. And so this was the prompt or the response it gave. We don't have to read it thoroughly, but as you can see, it is very accurate. It is able to describe how, we're plotting luminosity against spectral classification, and then it describes how the main sequence goes along the main diagonal, and then it talks about supergiants and giants along with white dwarfs, and it does a very good job at describing what these diagrams in and of themselves are, and what they represent, and how, we look and use them. Look at it. Yes, but based on that description, this is the image that it generated. And it follows a canonical shape. The spelling in this one is much worse than the other ones that we saw. The labels do not make sense, and it is just very incohesive and not useful in any type of like visualization.
To be clear, you took an HR diagram.
Yes.
It wrote that description.
Yes, yeah.
That description
So
back in. So this is the inversion.
Yes, essentially. So that's based on that description, this is what it generated. And then after bugging it, so originally I asked it, okay, now describe this particular image that you generated back to me. And the first description followed the same description that it gave for the other image. And so it doesn't actually go back and analyze this image until you start arguing with it. And then I had to prod at it several times and be like, no, go back to this image and actually like describe what it is that you generated. And eventually it was able to, I guess, conclude that, it did not do a good job. Although it does still, I guess, see this image as representing a plot from luminosity against temperature, and it says that it does so in a canonical manner. But it does say down here, like the background enhances this comprehensive diagram. Like, I think it's still very confident in what it has described, even though we are able to look at it and see that it is not useful. Yes. 4.0, yes. Yes, I should probably also preface that. But finally, after more iterations of argument, it finally does state that, The diagram blends scientific concepts with artistic visualization, prioritizing aesthetics while hinting at the relationship between stellar temperature, luminosity, and classification. And so it is not intuitive, and it does always offer to generate new images. The new images generated are very similar to the last, and so I don't think that through this iteration process it will learn unless done by millions of people across the globe several times, so that the image is actually flagged, so that the model is actually flagged on this and is able to, I guess, like realize in a sense. And then we worked on code generation. So this is the code that it generated for a simple HR diagram using matplotlib. And this is the original plot, which, as you can see, is inverted, and it only has one label on the temperature tick, so not very good. But after having it fix itself, it actually generated a pretty decent graph. And when we overlay it with an HR diagram, and we aligned, obviously, the X and the Y axes, you can see that it does follow the general shape of an HR diagram. The end half of the graph over here is not as maybe great as it could be towards the tail end, but it is pretty good for generating code, which we know that ChatGPT is very good at. But we asked ourselves, what could be going wrong? And so ChatGPT is DALL-E, which is the image generation that ChatGPT uses, is trained with CLIP, which is what is like the token embedder. So it is what turns these words into vectors, tokenizes them, and embeds them. And it's trained on over 400 million image text pairs. And they are trained, like it was created by OpenAI, but the training set is not released. So I'm not like, it was taken off the internet, so we can assume that most images on the internet have been used to train CLIP. But because it is, I guess, not based on academic papers and things that like we are used to in the astronomy field, the images that are being paired to certain text words could be, in a sense, convoluted and not as descriptive as we would like them to be as a field. And there is also a lack of descriptive astrophysical infographics on the web. So when you search up a Hertzsprung-Russell diagram, you will get a plethora of images, and you'll also get like a description of the stellar life cycle. But in terms of like the actual physical properties of the image, there's not a lot of description that comes into that. And CLIP's latent space is also based on the theme of the majority of its training set. So if majority of the training set is based on any picture, like art and nature or something of that sort, majority of the images that it generates will follow that theme. And so it could be why majority of these images have this kind of retro theme. And when I asked ChatGPT, what is the main difference between ChatGPT text and DALL-E's CLIP, this is a table that it generated, which I was actually very surprised by, and it's actually very good. And it does explain how, you know, the difference between why ChatGPT is able to create these text responses that are very accurate and useful, whereas DALL-E is not able to generate informative infographics. We see that the main differences is that when DALL-E is tokenizing, it does use a convoluted neural network, which is basically a filter applied to an image that is able to abstract like the main parts of an image, and then it uses a shared latent space for text and images, and so a lot of these things can get mixed together and kind of become like a soup, let's say. So yes, and I guess what might we do moving forward? This is you know, a beautiful HR diagram, and so what we can do potentially is go into CLIP's training set and include more training pairs of HR diagrams and other also astrophysical infographics, graphs, and diagrams, along with descriptive text pairs that are approved in an astronomical sense. And we can also be more descriptive of the images that we, you know, are releasing on the web as a field, which would obviously take some time, but it would definitely be helpful. And there's also a GitHub repo that was created by a group of coders on the web, that allows you to actually train your own model of DALL-E using PNGs and your own text descriptions. So we could, upload as many HR diagrams as we would like, along with our own text descriptions of these HR diagrams. And so potentially using this repo would give us a greater insight to see if DALL-E could potentially do these things. And so these are my references. And yeah, thank you. And then, these are who I work with. Thank you.
So, more questions about that one? No.
Very nice talk, but I have a question about whether you experimented more with the inversion when you were getting them. And what I mean by that is, did you try to see whether it's actually describing the image or whether it's still giving a lot of weight to texts that has been associated with this image? Because I've noticed in the past that if I trick it, it actually, you can tell how much weight it gives to an existing text.
Mm-hmm. That's actually a very good point. I think I've tried to, I have played around with, sorry, the microphone is kind of hearing myself through them. I'm just gonna protect my voice. So I have played around with it a lot. I guess the issue is, as you said, trying to really understand where, if it's giving the weight to existing text on the internet versus the actual image in and of itself. And I guess I tried honing out, down on the model a lot and being don't look kind of at textual resources, but really look at the image and physically describe the aspects, describe the axes, describe the color scales, describe the shapes.
So you told ChatGPT to do that?
Yeah. And it does sort of still provide the same textual response that you would expect, but it is able to kind of, with the particular HR diagram that I had shown, the black one with the colorful main sequence, etc. It was able to actually describe the color gradient and the shapes used and the different circle shapes used to describe the different sizes of stars. And it was able to describe how it uses a black image, black background in order for a crisper image. And it is able to describe the labels as well. I think it just requires a lot of argumentation with the model.
Right.
Yeah.
That's great. That's very valuable.
Yeah.
I have a follow-up question. Did you try a different LLM?
So we tried Claude, and Claude is really good at writing code as well, but the thing is that it does not actually generate an image, so to speak, or the diagram, it just does code, so what the last portion of ChatGPT did, and so I guess I really only focused on ChatGPT and DALL-E.
Unfortunately, we have to move on.
Okay. Hello everyone, my name is Hannah Burrows and I'm a junior studying astrophysics and earth and planetary sciences with a secondary in integrative biology. My project is called Characterizing the Molecular Complexity of the Planet Hosting Disk around HG 169142. And this semester I was looking at an area of active planetary formation and taking a look at the chemical complexity of this area, which can be connected with the physical dynamics of protoplanetary disks and also influence habitability of this planetary system. So looking at how planets form, it begins when a molecular cloud collapses during star formation. It forms this disk-like shape due to the conservation of angular momentum. And as that disk evolves, you get a protoplanetary disk, which is exactly what it sounds like, where planets are being formed and developed. And as the mass dissipates and these planets grow in size, you eventually get a planetary system like our own solar system. What about the chemistry and the complex chemistry within this system? We know a lot about planetary system chemistry due to our own solar system. We can observe comets here. You can see glycine in comets and stuff like that. And we know a lot about molecular clouds and protostars, but what about this intermediate stage where there's active planetary formation and these complex molecules are being actively accreted onto planets? So we have to take a look at protoplanetary disks for that. So these are several disk images showing the thermal emission from millimeter-sized dust grains. There's a lot of structural variation, as you can see, and a lot of this can be tied or induced by planetary formation. There's gaps, there's spiraling, there's warping, and some asymmetry.
So this forms, as we take a look at the disk structure and how that evolves, this typically start as kind of this flared shape of all the gas, dust, and ice it inherits from its parent molecular cloud. The temperature can range from 10 Kelvin in the outer disk to 10,000 Kelvin in the inner disk. Densities can also vary greatly between the disk and across disks, from 10 to the 6 molecules per centimeter cubed to 10 to the 12th per cubic centimeter. So these larger particles will drift towards the midplane due to gravity, the same way that planets do in our solar system. And material can also creep onto the star due to drag forces. So as this disk evolves, you have these grains growing in size, conglomerating together, eventually leading to planetesimal formation. Closer material falls into the star. And also influencing all this are these snow lines. So this is the threshold where molecules freeze out of the gas phase and onto dust particles that are already present. So for our solar system, the water snow line is about 2.7 AU, which is where the asteroid belt is, which is also why the asteroid belt is where it is. Our CO snow line is further out, closer to the orbit of Neptune. For the disk I'll be looking at is closer to 2 times the mass of our sun and has a further out water snow line at 10 AU and a further out carbon monoxide snow line at 100 AU. These snow lines are again important as they facilitate planet formation and can often lead to the formation of gas giants. So these gas giant planets are rapidly accreting material and they'll clear their orbit, which can cause gaps and spirals within the disk structure. The composition of this planet is also very dependent on the chemistry of where it forms and what it is accreting, which is different across the disk due to these small little dust grains. So complex chemistry usually occurs on these dust grains, especially on the ices that are frozen out onto it. They're layered in the order that these molecules condense. So you have silicate in the center, water-rich ice, and then carbon monoxide-rich ice. So this is where we make these larger complex molecules that you normally can't in the gas phase. It's usually by the hydrogenation of these ices. So these products can overcome their binding energy to the ice and be sublimated into gas that we can readily detect by either UV and cosmic rays, which can occur wherever in the disk. This is also known as non-thermal desorption. And you can also have heat or thermal desorption cause the sublimation of these complex ices, which occurs usually within the snow lines and about 100 Kelvin for our molecule of interest. So all these come together, all these chemical equations and all the sublimation to create our lovely methanol. Here's the equation in the top right. And methanol is really important for us because it's not just methanol that's we care about, it's everything that methanol is tied to. So methanol is a huge part of this giant complex chemical equation. And so if we see a high abundance of methanol, there's likely also an abundance of these larger molecules that may be still hidden in ices or too small to detect. So a lot of these larger molecules are called complex organic molecule, or COMs, as I'll be referring to them as. And they're these large molecules that have 6 or more atoms, and they're very essential in the pathway to larger prebiotic molecules. There's columns that also exist for pathways containing nitrogen and sulfur, which is really important because we have amino acids and DNA that contain both of those things. So this ties into my kind of the goals of my project, which are as follows: analyze ALMA data on the disk of interest here, detect what molecules are present there and what transition lines we see, and then constrain the properties of the COMs that we detect, so find their temperature, their column density, any other properties we can see. The disk I'll be looking at is a warmer Herbig disk. This picture here shows the thermal emission from the millimeter-sized dust grains again. It's pretty young, it's around 6 million years old, and is about 1.65 times the solar mass of our sun. It's a nearly face-on protoplanetary disk with only an inclination of 13 degrees, and it's 114 parsecs away, which makes it very easy to observe. Same with its warmer temperature, as you can resolve a lot closer to the sun in larger AU scales. We know methanol is there due to work that my advisor has done in 2023, but it's not yet quite characterized its temperature and the reserve of this methanol. This disk is also really interesting, especially for me, because there's potentially 2 gas giants within this disk over here in the 2 cavities. The larger one that we are most sure is present is likely around 37 AU from the center star and about 10 Jupiter masses or less. So you can see here are 3 different observations of this planet. You kind of see it's progressing through its orbit. Yeah.
So our data was taken by ALMA, which is the Atacama Large Millimeter Array. It's a radio interferometer. And we took a look at band 7, which is about 290 to 315 gigahertz. This is a new range of detection for this disk and allows us to see new kind of lines from these molecules. Our data has a resolution of 0.2 arc seconds squared, which is decent. And using these methods and large lengths ALMA, all of these molecules have been found in disks throughout our observations in general. And there's a lot more that we detected every year. There's more and more papers. This is kind of a very new field. So what does this data look like? The data from ALMA kind of comes in these image cubes where you have a 2D image and every single pixel has its own spectra, basically. And so you can do a lot with this. On the right, you can take an aperture, so the size of the disk, and create these spectra. And you'll notice a lot of them have these bimodal distributions. And that's because the gas in the disk is also rotating, so you'll have some of it Doppler shifted towards you and Doppler shifted away from you, creating this bimodal peak. I'll also show you guys some moment maps that we create by kind of collapsing along the frequencies or channels of interest. So you can see the whole distribution of these molecules. And you can kind of visualize these together easily. Here's a video straight from CASA of kind of one of the strongest lines we have. You'll see it has that kind of distribution as it goes along the frequency range. So here are the 6 methanol lines that we detected in this disk. There are a range of temperatures from 16 Kelvin to 180 Kelvin. And there's also the transition state listed below the temperature. This data is also double peaked, like I mentioned, due to the velocity dispersion. And also has this very interesting asymmetry that was present throughout all the different temperature ranges, which means it's likely from like a physical variation across the disk and less from like a thermal variation. To visualize this in another way, this is looking at the spatial distribution, those moment maps I showed earlier. You can see that methanol is typically a lot more compact, has about 50 AU scale, so it's usually within 25 AU of the star. And then we also found all these other molecules within this disk. We've known that these have been here before, but these are new detections and new lines that we looked at, which allows us to kind of constrain more about this reservoir. Here are maps of those molecules, and I'll highlight a few really interesting things to point out. Notice this is also a much larger scale, as these molecules are much more present and further out compared to methanol. So this CO line covers kind of a lower temperature range and generally traces like the bulk of the gas, especially beyond the water snow line, which is kind of where that gap is in the center, around like 20 AU, I believe. And these other more simple molecules kind of trace inside the snow line and outside of the snow line. So CS does kind of the outside. It's a very high flux measurement. You can see how smooth it is. And SO kind of traces within that snow line. This central row here is kind of these intermediate molecules. They're much less abundant, so a lot noisier data. But they kind of vaguely trace this kind of outer cavity space. So we need a little bit more high-resolution data on this to really see where they're present. And then formaldehyde is also very interesting because it's so essential in so many different pathways, even for methanol. So you can see it's very omnipresent throughout the disk. And as you increase in temperature on the right here, it's much more centered located around the star. It's also very peaked where we also detect methanol, which is very interesting. So going back to methanol, we're going to constrain the kind of characteristics about this disk. And luckily, we have our 6 methanol lines that we can use. I won't go too much into the math, but this is generally kind of used to fit our data to finding the column density and the rotational temperature of this methanol. It's kind of fitting for a straight line where the y-intercept is this column density, the second number there, and the slope relates to this rotational temperature. So kind of in line with what we expected to find, we found that this disk has a rotational temperature of about 95 Kelvin and a column density of 8 times 10 to the 14th per centimeter squared. So where is this methanol usually located? We used an area, it's like a ring-size annulus from 10 to 25 AU, or 0.08 arc seconds to 0.22 arc seconds, which is traced out by this paper, which uses these CO lines to kind of trace out where the hot gas is located and where this methanol is also subsequently located. So we kind of just did the full width maximum of this line here, and you can kind of see how that's traced out on one of our maps here. It's the dashed line in the center. So we kind of say that it's about compact in this area. So what do all these numbers mean? The column density is kind of a very big number that might seem incomprehensible to some of you. So to think of another context, this is the 1995 comet Halley-Bopp, where we detected methanol and other molecules in its evaporated trails. And the amount of methanol we found in this disk is the equivalent as this comet evaporating methanol for 700,000 years, which is a lot of methanol to be present in this planetary system. And looking at this compared to other protoplanetary disks that have found methanol, there's only 4 total, including HD 169142. There's TW Hydra, which is a much cooler low-mass star. So it's likely more dominated by non-thermal desorption. So the number density is smaller, and the rotational temperature is much smaller. And then these other 2 disks are much warmer, and they're also Herbig disks, like ours is. So they have similarly higher rotational temperatures and also similar order of magnitude of column density. So this brings us to kind of our key takeaways about this, is that we found our disk is a very warm disk with a small CO ice reservoir. Its CO snow line is likely past what we can observe. And so there's a lot of methanol, though. This could kind of support some things about inheritance and how protoplanetary disks can inherit things from their original parent molecular cloud. So yeah, this is also consistent with characterization of methanol with other Herbig worm disks, like the 2 we saw before, and reveals potential further chemical complexity within this disk. If we see a lot of methanol, what else are we not seeing that's still hidden and stuck to the ices? And kind of our next steps is we need kind of higher resolution, lower noise detection to find these weaker lines and to find exactly where they're coming from in these warm disks. More detections of other complex molecules, which will allow us to do the same thing we did with methanol of constraining its rotational temperature and also its column density. But yeah, I'd like to thank my advisors, Dr. Alice Booth and Dr. Karin Oberg, and my reader, David Wilner. And thank you to Alyssa Goodman and Doug Finkbeiner in Astro98, and all my peers in Astro98. Is there any questions?
I hope this was
Great. So, questions? Yes.
So that's really cool that you're able to find methanol in this disk, and it's similar to the other Herbig objects. I know you only have 3 data points, but was there any trend with like the methanol column density and the masses of these disks or the stars themselves?
I haven't looked into it too much, and I think one of this we have kind of varying ideas of what the rotation temperature actually is. So I think that my data point on my rotation temperature 95 is kind of within the margin of error of those other disks. I don't know if Alice remembers anything about the other disk that
Please go with that, Charles.
So I'm having difficulty formulating this question, so bear with me. You show spectroscopy taken from Alma. You pick out lots of lines, you identify lots of molecules. Are there still lots of other lines that you haven't been able to identify yet, or are you getting to the point where you're able to identify every strong spectral line in the
Yeah, for the most part, I was able to figure out which spectral line belonged to which one. It's more a matter of like multiple molecules kind of being nearby each other. There's a lot of lines that can happen from these organic molecules. So yeah.
But you're saying, could there still be stuff left over in all the blending that isn't being identified? Is that what you're asking?
That's what I'm asking.
Yeah, maybe.
Just question marks on this.
Yeah. And there's also some fitting you can do to kind of help with the noise ratio, so you can detect a lot of weaker molecules.
Amazing data. We have one last question? Yeah.
It seems the only isotopal log that was detected is the 13CO or maybe C18O. But I was curious about any other among molecules like methanol, for example. Do you have any isotopal log detections of those?
Yes, I didn't focus on those specifically because those have been previously detected. Here, if I can find them. It was kind of the paper I used to base off of where to restrict my methanol location to be. So they also look at different CO isotopes here and different CO lines.
Fantastic. Okay, so let's thank Hannah again.
I also want to quickly mention the title of my presentation is actually slightly different than what's on the schedule, just because there were some issues with data that I ended up having to change the scope. But yeah, so hi, I'm Sophia Magaro, and I'll be talking about my comparative study on Einstein radii and gravitational lenses. I was advised by Kim V. Tran. And yeah, so I first wanted to give a little background on like what gravitational lenses are, some like historical context, what they are, some applications. Oh, I can hear myself. So first off, what is a gravitational lens? So gravitational lenses essentially have light from a source object that get bent around a deflector object due to the gravitational force. And then we see a distorted object from that source object. So in this image, for example, the galaxy on the left would be our source object. The galaxy in the middle is our deflector object that's causing the gravitational force on the light from the source object. And then we on Earth see the image itself. So it would look something like that image on the right. In gravitational lensing, we have three main types. We have micro, weak, and strong lensing. In this talk, I'll be talking about strong lensing in particular, which gives us clear arcs and multiple images of the source object. For some historical context on the background of gravitational lenses in the field and how we got here, the idea was first verbalized in like the 1700s by Isaac Newton, where he presented the idea of light being impacted by gravity, but nothing really came of that until like 200 years later, where microgravitational lensing was first observed. In this situation, we had a solar eclipse, and when the solar eclipse was happening, there was a very slight change in the star positions in the background, and microgravitational lensing is on the star like scale. However, Einstein theorized that it could be bigger than just stars that cause this like movement and this lensing, and galaxies itself could also do that. And it took a while for this to be observed, but like 45 years later, strong gravitational lensing was first observed. This was a system with quasars where it looked like there was two identical quasars right next to each other, but it turns out that they were actually just, it was a lens object and it was a multiple of the same image. Since then, it took a while for lenses to be more commonly discovered, but by the 2000s, lenses started to be more commonly discovered, and now we have like systems in place for how to discover lenses and what it means for like how would you even find a lens? So some applications of gravitational lenses, because you might be like, where would these ever come into play? So first example would be Hubble's constant and Hubble's tension. With finding Hubble's constant, the way of doing that is with time delay cosmography. In time delay cosmography, we have time delay distances, which are inversely proportional to Hubble's constant, as we see on the left, or right? And one model that we can use to find time delay distances is gravitational lenses. As we see on the left, basically, the distances are referencing distances within our gravitational lens model. And within a gravitational lens, the light that's coming, the deflected light from the source that's coming around the deflector, there's a slight time delay in when we actually on Earth receive the light. And so with that, we can find the time delay distance, which allows us to constrain the Hubble's constant. Another use of gravitational lenses is with dark matter estimations. Using a similar model, and as you can see, a similar equation, we can find the total mass in gravitational lens system. And it turns out it's also not horribly difficult to find the stellar mass in gravitational lens systems, which allows us to find the dark matter in these. And lastly, another use of gravitational lenses is in galaxy evolution, because it lets us look so far into the early universe by letting us see objects that we wouldn't otherwise have been able to see. Gravitational lensing is also a good use for that. But within gravitational lenses as a model, we need to also look at Einstein radii, because it basically tells us what is the size of this gravitational lens. It helps us determine basically what the lens is. So what are Einstein radii? In a gravitational lens, we generally have something that's like the main image and the counter image, though this does differ per lens that we look at. In this image of the lens, for example, the main and counter image kind of combine to be like almost a ring. But if we are looking at an image of a lens, we can observationally measure the Einstein radius just by finding the radius of the ring that's on there. You could also do this but with a line if it's a slightly distorted ring, like in this case, and just take half the distance of the line, and that would be our Einstein radii for this lens. Though again, this does differ per lens that we look at, and we have to determine what the best method is for observational measurements per lens. We can also calculate this mathematically, however, if we have the total mass and the distances around the lens with this equation here. And what this gives us is if, for example, if we have total mass and the distances, we can find the Einstein radii. But if we just measure the Einstein radii and we have the distances, we can find the total mass, which again is helpful for some of our applications. And I wanted to talk a little bit about the data sets that I worked with. The ACS data set, which is advanced cameras for survey. And I looked at this one. I had some data from here. It was around 40 lenses. Not a complete data set, but it's what I had to work with. I measured the Einstein radii of these, and I compared that with the WFC3 camera work, which is the wide field camera. One of my teammates, Lena, worked on this over the summer. She modeled around 10 to 20 of these lenses and got really accurate measurements of the Einstein radii. So my goal was to compare the ACS with the WFC3 data. I do want to note that these gravitational lens data sets are rather small due to, one, the fact that these data sets are not complete. They're not an entire list of every single lens that we know of. But also, gravitational lenses are pretty rare. If you think about it, gravitational lenses are on the order of like a few square arc seconds, whereas the sky is like a billion of square arc seconds or so. And so having the chance of having two objects line up enough to create a lens is very rare when you're looking at the sky. I wanted to also note that there was one application I looked at that I couldn't really look too much into due to a lack of data. Basically for this, it's a probability plot of finding lenses with certain source and deflector redshifts. However, I didn't have too much source and deflector redshifts of the ACS data, but I did want to note that I did add my data to this, and it gives a little more context as to what this plot is representing. But I won't talk too much on this because I couldn't do all that much with it. But how did I actually go about comparing ACS and WFC3? So WFC3, Einstein radii, I already had those. They're in a list. They're lovely, amazing. To measure the ACS data, I could either go about modeling like Lena had previously with the WFC3, or I could hand measure. And unfortunately, due to time constraints, I ended up having to go with the hand measurements. There's a software called DS9 that allows us to actually upload the raw files that we had to visually see the gravitational lenses. You have to play around a little bit with the viewing settings, but I got mine to look like the image on the left. You can pretty clearly see what the different parts are as such. We have the main image, the deflector, and the counter image. And because in this case, the counter image and the main image are both pretty similar distance from the deflector, I just use a circle to measure the Einstein radius, but for different lenses, you have to use different tactics. But for this one, you get to use a lovely circle. And I did this for each of the 40 lenses that I had, and I noted down all the Einstein radii that I had. So how did I actually, in the comparisons with ACS, with WFC3, I was specifically looking at single source lenses, so lenses that particularly had a galaxy as a deflector rather than a cluster of galaxies, as well as lenses that had an accurate Einstein radii measurement. So for the ACS one, that ended up being around 30 lenses, and the WFC3, that was 19 lenses. I created these histograms describing the number of lenses that we found in each of the data sets with specific groupings of radii, and I calculated the mean Einstein radii and the ranges of the radii, and I got these values. And using like a statistical analysis test, we determined that these are fairly similar results and not statistically significant differences. And so we call them they're statistically comparable data sets. But I did want to note that with the ACS data set, we do believe that it's probably a bit of an overestimation because sometimes when the counter image, it blends in with the deflector in the DS9 software, so it's a little hard to decipher. So we do believe it's a little bit of an overestimation, but they still do overlap, so we do still consider them comparable. No, they're separate. There might be a maximum one overlap. I highly doubt. Oh, they're different cameras, so there shouldn't be any overlap.
Well, no, I mean, which lens are you looking at? Not which camera.
Oh, I believe these should still be different, or mostly different lenses. There might be
different sources. I don't, by lens, I mean, what source on the sky? I mean, is there an overlap between the sources on the sky?
I was looking at, I don't recall seeing many overlaps, especially because I'll get into it later, but most of the WFC3 data has spectra available, and most of the ACS does not have spectra available, so I would consider them almost likely different. So there should be very little overlap in these. But yeah, that was the results that I got for the comparisons, and we believe that they should be statistically comparable, which allows us to use these both interchangeably with our comparisons. However, there's a lot of limitations with this. The scope of the data set and limited number of lenses, because these are not completely full lists of all the lenses that exist that we have found, it's a pretty limited number. And also, there's not very many spectra available, especially for the ACS data set. There was 4 or 5
lenses that had spectra available. So the comparison I was trying to look at earlier, I couldn't look too much into it just because we don't have the data available. But that having a knowledge of those limitations is helpful because for future proposals we can ask, we need the spectra so that we can actually look at what we want to look at, or just being able to know that there might be some uncertainties here. And again, with hand measurements, they're often not perfect. We predicted an overestimation, but again, for our purposes of comparing the two data sets, they are close enough. I did look a little bit into the dark matter estimations, as is evident from the different title. I won't talk too much into this just because, again, there's a lack of data. I need the spectral redshifts of the source and deflector, but also the R band magnitude, which gives one less lens in the ACS data set. We can use Einstein radii as well as redshifts to determine the total mass of our gravitational lenses. Stellar mass is where I had a lot of issues because you basically need a luminosity to stellar mass ratio, which it's a little bit complicated to figure out, and I'm not exactly sure how I would do that, but with some really, really rough estimations, I determined there's probably around 95% dark matter in these systems with probably around 10% of uncertainty. But it is interesting to know that like with these gravitational lenses, I can still determine what the proportion of dark matter is in these systems. But yeah, that's all the work I did for this. To summarize, I manually measured the Einstein radii of the ACS data. I compared that to the WFC3 data and determined they are statistically comparable. And then I analyzed some further applications of gravitational lenses with the ACS data. And given the future existence of some spectra of this data, we can further analyze that and actually get some concrete numbers. But yeah, I just want to thank my research team, my professors, my class, for giving me comments every week. And yeah, thank you so much all for coming to my presentation. And if you wanted to look further into anything, I have some references. So yeah.
Will the lights work?
Oh.
We can have only on or off.
No options.
It's like, okay, whoa, so
Sorry.
questions for Sophie, sorry about that.
Are there any questions?
Yeah.
So for the two comparison, are you looking at the same part of the sky?
I think it's all over the sky. I also did note down, I don't have them on here, but I do have the RA declination of each of the lenses. They do range across the sky. They're not all in the exact same area, but yeah.
Do you find the same objects? I mean, do you have any?
I highly doubt there's that many overlaps between them just because there's more information available for the WFC3 data than the ACS. And basically the team that I'm working with has like this giant database of all the lenses that we've looked at. And most of the ACS lenses are not on there with the spectra. So whereas the WFC3 data has a lot of spectra available. So I don't think that there is much overlap with that.
Yeah. I was wondering if we knew why the distributions peak at like 2 to 3 Einstein radii?
Yeah, so these are single source lenses. I didn't look too much into like how we determined what the average of these, so let me actually just go back to that. Basically with single source lenses, just the average, or let me actually go back to, where was it? So in this, basically what this is saying is that the closer and further that the distances between, this is the distance to the deflector object, this is the distance to the source object, and this is the distance between the source and deflector object. And just specifically with single source lenses, it just happens to be that the ratios of this that are needed to have single source lenses actually visible means that it's around 2 to 3 arc seconds of radius around the deflector. I don't know if people on my team
Are you saying, to follow up on this question, are you saying it's a selection bias, that this would be some distribution that was sort of the same number of radii all over the sky?
It's more that if it's more if the source is even further away than it is right now from the deflector galaxy, that the ring will become so big that it's not really even visible anymore. So in order for the ring to be visible, it's required that it's within like a certain range, which happens to be around 2 to 3 arc seconds of deflection.
Makes sense, thank you.
With the data that I'm looking at, again, not a complete data set, it does turn out to be a little lower than 2, I believe, for the average, but yeah.
Great, okay, well, I think to keep us on schedule, I'm just gonna say thank you very much and ask Ashini.
Hi everyone, my name is Ashini. I'm currently a junior at the college studying astrophysics and biochemistry, and today I'm going to be talking about my work over the past 2 months.
on modeling the angular momentum loss of cataclysmic variable stars to try and reproduce the orbital period gap. So what are cataclysmic variable stars? They are semi-detached interacting binary stars. So essentially you have a secondary star, which is a low mass main sequence star, and then you also have a white dwarf. And surrounding them is what's known as a Roche lobe. So the Roche lobe is the region around the stars that are completely gravitationally bound by the star. So essentially what happens is when your secondary star becomes big enough that it expands beyond its Roche lobe, it begins transferring mass onto the white dwarf. And the white dwarf, as you can see here, is surrounded by an accretion disk. And when mass gets transferred around this accretion disk, we observe things that cause the cataclysmic variable star to become observable. So you get these like accretion outflows, and you get electromagnetic radiation, which you can observe as the cataclysmic variable star. So the secondary star can have masses from around 0.1 to 0.8 solar masses, and the primary star, the white dwarf, can have masses from 0.5 to 1.4 solar masses, with around like a medium mass of 0.8 solar masses. So the main thing that drives evolution of cataclysmic variable stars is angular momentum loss. But the mechanisms behind how this happens is still a little bit poorly understood physically. The two main contributions to angular momentum loss are gravitational radiation and magnetic braking. So gravitational radiation operates at periods that are lower than 3 hours, so sort of in the later stages of evolution of the cataclysmic variable star, whereas magnetic braking operates most strongly at periods greater than 3 hours, sort of early on in the cataclysmic variable star's evolution. Gravitational radiation is essentially when the binary star system has a quadrupole moment. Variations in the quadrupole moment essentially cause gravitational radiation to be emitted from the binary star system, causing angular momentum and energy to be lost. This essentially causes the orbital period of the stellar system to decrease. Magnetic braking couples stellar winds of the donor star to its magnetic field. So when you have mass that gets lost from your donor star, it essentially gets wrapped around that donor star as the star rotates. And it does that because it gets coupled to that magnetic field lines. And that causes sort of a torque around that donor star. And what that does is it slows down the rotation of the donor star. But because the donor star is tidally coupled to the white dwarf, it causes a loss of angular momentum from the binary star system as a whole, causing a decrease in orbital period of the binary star system. So essentially, mass coupled to the magnetic field carries angular momentum loss away from the binary star system. So now let's dive a little bit more deeply into how exactly angular momentum loss and mass transfer causes cataclysmic variable stars to evolve with time. So in the beginning of the evolution of a cataclysmic variable star, you have very strong magnetic braking. So this mass transfer along the magnetic field lines is very strong, so material escapes along the field lines, and you get angular momentum loss of your stellar system. This angular momentum loss causes the orbital period of the cataclysmic variable star and the Roche lobe to shrink. As the Roche lobe shrinks, you can imagine that the donor star is now starting to fill the Roche lobe. So there's material of the donor star that's expanding beyond sort of the gravitational influence of that star, and that causes mass to transfer from your donor star onto your white dwarf. And it is at this period that your cataclysmic variable star becomes observable, because you're getting these accretion-driven outbursts, you're getting electromagnetic radiation that occurs as a result of the mass being transferred from the donor star to the receiving star, which is the white dwarf. Now, as the mass transfers from the donor star to the accreting star, the donor star starts to lose mass. And when the donor star reaches a mass of around 0.3 solar masses, it becomes known as fully convective. So fully convective stars lack a radiative core. So this really sharp change in the physical properties of the donor star causes it to sort of undergo this thermal equilibrium process, which allows it to contract. When that donor star contracts, it detaches from its Roche lobe. And when it detaches from the Roche lobe, it becomes no longer able to transfer mass onto the white dwarf. So as you can see in that picture here, now our star is smaller than its Roche lobe, and it's no longer donating mass to the white dwarf. So because no mass transfer is happening now, the cataclysmic variable star becomes not observable, because we're not getting any of these mass transfer-related accretion-driven outbursts. Now, much later on in the cataclysmic variable star's evolution, gravitational radiation kicks in and becomes the dominant sort of founder of angular momentum loss. And gravitational radiation causes the orbital period and Roche lobe to once again decrease. And so as a result, the star begins to overflow its Roche lobe again, causing mass transfer onto the white dwarf. And at around 2 hours, the donor star contacts the Roche lobe again, and mass transfer resumes, and the cataclysmic variable star becomes observable once more. Now I want to dive a little bit more deeper into 2 specific steps that I talked about here. So the really critical time period in the cataclysmic variable star's evolution is this fully convective boundary transition. So as I said here, the donor star fills its Roche lobe, mass transfer occurs, cataclysmic variable star is observable. But then at a certain point, what happens is your donor star, detaches from its Roche lobe and mass transfer stops. So this transition here is extremely critical and can help us really understand how cataclysmic variable stars evolve and the contributions of angular momentum loss for this transition. So I briefly mentioned the fully convective stars lack a tachocline. So this is the interface between a radiative core and a convective envelope. And because we don't really have this radiative core anymore, and the radiative core is what drives the magnetic dynamo, you get weaker, less organized, larger scale, more complex magnetic fields. Because you have more complex magnetic fields, they're less concentrated, and magnetic braking becomes much less efficient for fully convective stars. As a result of this magnetic braking becoming less efficient, angular momentum loss slows down significantly. Now, in this region, when your star, overflows its Roche lobe and then detaches from the Roche lobe due to this change in magnetic braking efficiency, we get something known as a period gap. So that region where the star is no longer overflowing its Roche lobe occurs supposedly between a period of 2 to 3 hours. So as you can see in this diagram here on the left, you see a notable paucity of systems between 2 to 3 hours. So there's not as many systems there, but before and above the period gap, there are lots of cataclysmic variable stars that have been observed. And in this histogram here, you see the exact same thing, where between 2 to 3 hours, there's a lack of observed cataclysmic variable stars. And the standard theory for this attributes this period gap between 2 to 3 hours to changes in the angular momentum loss mechanisms that drive the evolution of cataclysmic variable stars. So angular momentum loss, like I said, around this region of 2 to 3 hours and before that is strongly dependent on the magnetic braking of the cataclysmic variable stars. So lots of previous papers and research have suggested that there is a sharp reduction in magnetic braking and therefore angular momentum loss efficiency when the star becomes fully convective. And the papers that have described that in a lot of detail are cited there. But this very abrupt change in magnetic braking that you can see in the top graph there may not be necessarily visible. So lots of papers have come out proposing the evolution of magnetic braking with magnetic complexity. So one particular paper is García et al. 2016, which proposes this evolution with higher order magnetic complexity. So as you increase magnetic complexity, you get a decrease in angular momentum loss rate because stars with higher order multiple fields exhibit weaker angular momentum loss. So this sort of gradual transition in angular momentum loss with magnetic complexity may be able to explain the period gap. So here in this research, I used detailed binary evolution MESA simulations to investigate whether various angular momentum loss models can reproduce the period gap from 2 to 3 hours that we're seeing in cataclysmic variable star systems with realistic stellar evolution modules. So the parameters that I use, so MESA is a software, modules for experiments in stellar astrophysics. Essentially, in this software, I turned off all angular momentum loss contributions except those from magnetic braking. So this includes turning off gravitational radiation. This is because we really wanted to hone in on magnetic braking specifically because that's what's dominant around these regions of time that we're interested in. I also set the white dwarf mass to 0.82 solar masses, the donor star mass to 0.65 solar masses, and an initial orbital period to 6 hours based on previous research papers. So the first angular momentum loss model that I decided to look at was the Rappaport-Verbutt and Joss 1983 model. So this model, you can see the formula for torque due to magnetic braking there on the right, essentially scales the magnetic braking torque with omega, so with the angular velocity. So as you can see, it's scaled with omega cubed, meaning that angular momentum loss is strongly enhanced for faster rotating stars. So that's what's really key about this model here. And in the top graph, you see age on the x-axis and the angular momentum loss rate on the y-axis. And you can see that as we increase age in early time periods, you have an increase in angular momentum loss rate. But then over time, as the star, reaches its Roche lobe, starts transferring mass onto the white dwarf, it loses mass, and that leads to a reduction in angular momentum loss rate over time. But with this model, without any really sharp decrease in angular momentum loss rate, you get really high mass transfer throughout all time. So especially with this period gap from 3 to 2 hours, there's a really high mass transfer during the period gap. So this really shows that you probably need a strong decrease in angular momentum loss rate at that fully convective boundary in order to get a reduction of mass transfer to possibly explain the period gap. So what we do next is we reduce the angular momentum loss rate due to magnetic braking at the fully convective boundary, and we reduce it by 90%. So it's still using the exact same model, except at the convective boundary of 0.3 solar masses, we reduce it by 90%. And you can see that reduction on that top graph here, where as we get to the fully convective boundary, there is a very sharp decrease in magnetic braking, leading to a very sharp decrease in angular momentum loss rate. On the bottom graph, you can see the evolution of the star overflowing its Roche lobe. So in the beginning, it increases, contacts the Roche lobe. When it sufficiently expands, begins transferring mass. But then as we shut off angular momentum loss rate, the star detaches from its Roche lobe, no longer overflows, and then it picks back up again because of the very weak magnetic braking. So it's only shut off by 90%. There is still some there, and it's able to recontact its Roche lobe. So given this new formalism, by decreasing mass loss rate, or angular momentum loss rate, by 90% at the fully convective boundary, we do get a very sharp decrease in mass transfer. So here you can see there's a decrease in mass transfer around the sort of 2 to 3 hour period range. However, it's not exactly in the 2 to 3 hour period gap that we're seeing for cataclysmic variable star systems. It starts a little bit before at 3.3 and ends a little bit before at 2.5. So this suggests that the strength of the magnetic braking may perhaps play some role in where we're seeing this decrease in mass transfer start. So to see whether or not any sort of reduction of the baseline magnetic braking strength that we're starting off with changes where this period gap occurs, we decrease the baseline J.MB by 2 times. You get the same pattern where you have that decrease by 90%, leading to detachment from the Roche lobe and a lower Roche lobe overflow. And interestingly, you do see that now you see a decrease in mass transfer exactly at the 3 hour period boundary, but it still only goes to around 2.4. So still some playing around with this model needs to be done to see how changing the baseline magnetic braking strength may or may not expand this period gap that we're seeing, and even playing around with different stellar masses to see how that also affects the gap in mass transfer rate that we're seeing in the periods at which it starts and ends. At the same time, we are working with implementing the Garofalo 2016 angular momentum loss model into MESA. So here are some key formulas for this model. Essentially, the angular momentum loss rate is scaled with convective turnover time and magnetic complexity. The formula for magnetic complexity, which is N here, is scaled with the Rossby number. So the Rossby number is the rotation period of the star divided by the convective turnover time. And essentially, on the green graph at the bottom, you can see that as age increases, you get an increase in magnetic complexity. This is due to a decrease in Rossby number, due to a decrease in orbital period. And when you increase magnetic complexity, you get a decrease at the very top graph in angular momentum loss rate. However, this slight decrease in angular momentum loss rate is not sharp enough to cause any detachment from the Roche lobe. So you still see very high mass transfer throughout until very, very old ages, which is way past the periods that we're interested in. So on this graph here, you can see during the period of 3 to 2 hours, using this model with the specific parameters that we use, you still have very high mass transfer all throughout this period range. So this model, with the parameters that we used to produce these graphs, the mass transfer stayed very strong during the period gap. So in conclusion, we modeled cataclysmic variable star systems with various AML prescriptions with realistic stellar evolution. We found that a sharp drop in angular momentum loss rate is required to significantly reduce mass transfer. And we first used the Rappaport-Verbrugge and Joss 1983 model and showed that with a 90% reduction in angular momentum loss rate, you do get a decrease in mass transfer between around 2.5 to 3.2 hours. We're still playing around with initial strengths of magnetic braking. Also using the Grapho 2016 model, we found that mass transfer is continuously high, meaning that an increase in magnetic complexity isn't really sufficient to explain the period gap with these starting conditions. In the future, we're going to modulate the baseline starting conditions for magnetic braking, also adjust the A and B parameters for magnetic complexity to see if like a sharper drop in angular momentum loss results, and vary the starting masses of white dwarf and donor stars, and potentially simulating a larger population of cataclysmic variable stars to see if we get that sort of gap between 2 to 3 hours. I would really like to thank my PI, Dr. Garafo, also Seth and Jeremy for all of their help and all of their advising, Phil for agreeing to be a reader for the project, Alyssa and Doug for leading Astro98 and the rest of the Astro98 cohort. Here are my references, and I'm open for any questions.
Oh, somebody put the mic on. Amazing. Okay, great. So, questions? Yes.
So, just thinking about your last point about what's next and running a larger suite of simulations, how long does it take to run one of these simulations in Mesa?
That's a great question. So it really depends on what kind of computer you're running it on. So on my laptop, which is now fully out of storage space, it took me around like 6 hours to run like one simulation, and that wasn't even until the simulation that I ran for 6 hours didn't even reach the 2 to 3 hour period range, starting at 6 hours. So we actually ended up running it on Seth's computer, which is a desktop, and it took like 2 hours to run that simulation, but it still takes a significant amount of time. And so we're thinking about like getting a different computer so I can actually run these and not completely run out of storage. My computer is now showing lines on it, so probably not good.
I can ask one question. I'm curious, this is all sort of for Cecilia too, like the model that you explained, Cecilia's 2016 model, seems like it's a kind of continuous process, right? Where if you make things complicated, it's harder to make the math. So how would you get a discontinuous drop from that model?
Yeah, so I mean, the point of this model is that it's not exactly a sharp decrease in angular momentum loss, right? So like previous models would suggest like exactly when the star reaches that fully convective boundary, you get that 90% decrease. Instead, this one is proposing a more gradual change and hoping that this gradual change, it's still like supposedly a sharp change, but you know, it's more of a gradual change that
weird
evolves.
because on the graph you showed at the very beginning that had the graph and the histogram to show the gap, or was it?
Yes.
Yeah, that one. Like it looks much more pronounced on the histogram. And what are those open circles on the graph on the left? Do you know?
That is a great question. I think the open circles are...
Because those are in that gap, right?
Yeah, they are in that gap. I'm not actually sure what the open circles are. I think that that's just representing that there's a lack of systems there. I'm not entirely sure what the...
Because like on the one hand, that looks like a real gap. On the other hand, if those are real points, I'm a little confused. So.
Yeah, I think that like these points here are... Yeah, that's a great question. I think that like you can see above the gap, the points are colored in, and below they're also colored in, but here they're not colored in. So I assume that was, yeah,
I don't know.
Not entirely sure. But yes, on the histogram you can see that there is a like paucity of systems between 2 to 3. But I mean, like it's also interesting because like you can notice that as you like approach the period gap, it also becomes slower. So that might like suggest some sort of like gradual change in magnetic complexity as well.
Okay, well, thank you again. That was really good. And then we have Sol, who randomly wound up last and has been so patient this whole time. Thank you. The order of the talks was essentially random. Sorry, Sol. But thank you all for listening. And feel free to have more teams. Just ignore that.
Oh, it's okay.
Yeah, just say quit. Or that's fine.
Okay.
Okay. There.
Okay. Hi, everyone. So my name is Sol. I'm a junior, and I study physics, astro, and math at Harvard College. And I'm currently working with Michael Johnson and Daniel Palumbo at the Black Hole Initiative in the CFA. And our project is basically just like the role of interferometric phase when trying to measure black hole spin. So this image, or these two images, are probably familiar to most people here. They're some of the first images ever taken of black holes. And here, you can see the lines, that's just polarization. The way these images were taken were like using, through the Event Horizon Telescope collaboration, which is basically this like global network of telescopes that they all focus on one object at the same time, like during some, like a week-long observation period or something like that. Then you correlate all the data and you try to reconstruct the image that emitted all of these waves. And basically the next phase of the project, hopefully, is to extend this into space by launching a satellite, putting it into orbit, and then like the important part here, I'll talk about this in a second, but the important part is that the distances between like, a telescope in space and any telescope on Earth is going to be very, very big, and this allows us to just like observe much finer features of the black hole, such as the black hole's photon ring. And a photon ring is basically just like, you can imagine photons, light rays, traveling past the black hole, being slingshotted around by its gravity and then shot towards Earth. And the parameters for this to happen are so tight, so constraining. If the photon is slightly, like its trajectory is slightly off, it'll either shoot out to infinity or be swallowed by the black hole. So that means that we get a very, very fine, thin ring of emission, and its shape and other, if it's warped, if it's shifted, that can tell you a lot about the properties of the black hole itself and the space-time around it. But there's a nifty animation to illustrate all this. So here are the photons. This is the direct image. Nothing has been slingshotted around fully. And so this is sort of the initial accretion disk that we've observed, and this is like the image that's sort of familiar. And then next, you see what happens when the photons actually just like orbit the black hole and then slingshot towards the Earth. So you get this much finer ring that's called the n=1 ring. That's the first photon ring. And when we say n=0, that's the accretion disk. It's very blurry, very bright. Okay, so how do we actually, what does this kind of data actually look like? The observations that we're conducting are through interferometric phase. So that means that we're not, when you get data, you're not actually looking at a picture. You're looking at sort of this spatial decomposition of frequencies of all these light waves, all these interference patterns from a particular source. So just, for context and to be clear on terminology, when I say visibility response, I'm referring to the spatial Fourier decomposition of all of the light that we're receiving in the sky. And I'm not going to use coordinates x or y. That's those are the image coordinates. I'm going to be using rho and phi, or u and v, rho and alpha. Those are my Fourier transform coordinates. And basically, the way to think about it is just if you have some sort of source over here, and it's emitting light, and it's hitting the Earth, and you have these two telescopes, if you just project the distance or the line joining the two telescopes onto the plane perpendicular to your line of sight with the object, that'll give you this new sort of Fourier transform coordinate. That's the baseline. And the length of rho is what we really, really care about. We want rho to be as long as possible, basically, to observe very fine features. So these are some Fourier responses of very basic, very stripped down objects. The first one is the delta ring. So if you just imagine an infinitesimally thin ring of emission in the sky, this is its Fourier decomposition. It's a Bessel function. It's actually the amplitude. It's not, a Bessel function goes up and down. It's negative as well. But here I've taken the amplitude. And sort of the orange line is just how it decays at very, very long baselines. And then down here is the uniform disk. You can imagine that these are both they're very simple shapes, but they're pretty relevant when you're observing a black hole. Especially if you're looking at a photon ring, you can essentially model it as a delta ring and still extract useful information from that. So what is the actual motivation and what are the goals of my project? Basically, we tried to focus just on what information you can extract from the complex phase of the visibility. And phase is particularly powerful because it essentially allows us to perhaps bypass, in some way, the problem of interstellar scattering. This is because a lot of the, modeling interstellar scattering is very, very difficult. It's a worthwhile endeavor. It's very important, but it's very, very difficult. But fortunately, it doesn't actually affect the phase of the signal that you get too much. So if you just sort of subtract those models from the data to get your actual your actual signal from the black hole, the phase of this data should not be so effective. So if you just look at phase in the first place and you don't really care about the amplitudes, you can just sort of like skip the problem altogether. And then sort of the other part, the other aspect is looking at black hole spin. So black holes do spin, and when they spin, the kind of effects that this has on like the space-time around it sort of shifts the black hole to one side, and it like squishes it a little bit. And so we would expect that these kinds of effects have some sort of representation in the Fourier domain. So the goals, again, are just the distortion, like let's characterize the distortions of black hole spin, and let's see if we can sort of study them, reproduce them using first very simple geometric models. So we're literally just gonna like plot delta rings and then superimpose them and then just do funky stuff to them and see what their Fourier response is. And then, are these effects actually observable? And to do that, I essentially ran like fake observations on fake data. And then finally, like you can create much more realistic pictures of a black hole. You can factor in magnetic field lines, polarization. You can change the angle of inclination. You can make it spin up, spin down. And those give you much more complete, comprehensive pictures. So first, the one ring. Please humor me. And basically, this is like a pedagogical figure because we can't, like this tells us about absolute properties. I'll talk more about that later. But this is just for context. This is just for a little bit of intuition. So up on the left is the visibility response for a single ring, and this takes into account like what happens if you sort of shift it to one side and if you squish it a little bit. You can see, so basically like if you don't do anything to a ring, if you just take its Fourier response, because it's like decomposition is a Bessel function, Bessel functions don't have any complex phase, they're just real. So their phase, I guess in that case, would oscillate between 0 and pi. But if you take it and you sort of shift it to one side, you're going to immediately get this sort of like rainbow gradient because you will now introduce a complex phase. So the plots up here, the colors represent the phase. So I think blue is 0. Like the colder you get, it's the closer you get to 0, and then the warmer you get, the closer you get to pi or minus pi. And up on the top is what happens when you sort of shift the ring by increasing amounts. In the middle is what happens if you don't shift the ring, but you sort of compress it horizontally in the image domain. That means in the Fourier domain, you're going to squish it. Compress it vertically, and then in the Fourier domain, you're going to sort of compress it horizontally a little bit. And then the bottom row is what happens if you both shift and you stretch it. And then here, these graphs correspond to if we just sort of fix one distance, like some radius in the Fourier domain, and then we sample the interferometric response at that fixed radius, what is the phase along that circle that we sample? And so if we didn't do anything to the ring, you wouldn't expect to see any, you would just get a straight line for any of these plots, because you wouldn't expect to see any variation in phase at all. But you can see that none of these plots are a straight line. So that means that like even the slightest effects will create like all kinds of variation along some sample circle of the phase. But we really care about two rings because an interesting property about like interferometry is that you can't really discern like absolute properties. Like if you take a ring and you move it to one side, you can't, unless you have some object that tells you like this is your reference point and this is how much I'm shifting it from that object. If there's no second object, you can't really you can't discern a quantity like that. But fortunately, like the whole point of BEX is that we can now observe not just the n equals 0, but also the n equals 1 ring. So we do have like a relative source to compare to. And so what we want to try to model is what are the relative properties between the photon ring, the n equals 1, and the accretion disk, so n equals 0. The visibility response becomes a little more complicated, but it's really not that bad. It's just you take two geometric rings and then you superimpose them. And then you can blur them by different amounts. You want the accretion disk to be very blurry. You want it to be very bright. And you want the photon ring to be very, very thin, much less bright, about 10 times less bright. And you want the photon ring to sort of shift, and you want to squish it because, you want to shift it and you want to squish it. And so these are similar plots to the last page. On the top, I shift. On the middle line, I squish. And then in the third line, I squish and I shift. And you can see that it creates all kinds of variation in the phase response, and the plots, are they're pretty crazy. And so the next question is, can we actually observe any of these effects, and are they useful for trying to pinpoint whether or not a black hole is spinning or not? So just right off the bat, there's hope, because if you just sort of slap the trajectory of the EHT and BEX onto any one of these phase plots, you would expect to get a very decent sample of the interferometric, or the variability in the phase along an orbit. And so the next phase of the project was just, if you basically generate these geometric models, like a blurry ring and a very sharp ring, and then feed it to some program, and then say okay, let's run fake observations on this fake data. This is what's in the sky, and now from this, using only phase, not taking into account at all the amplitude of the signals, can it reconstruct properties of the n=1 ring, such as its flux, its angular diameter, its relative blurring compared to the accretion disk, and can it tell, the most important part were these two boxes, which are, what is the stretch position angle, and what is the displacement from the centroid of the n=0? Because these two properties in particular are the ones that we would associate to black holes having spin. And it did a very good job. It was very accurate. Interestingly enough, the EHT also actually does a good job, but it's just this is much more precise. These parameters are just much more constrained. But again, so far we only used very stripped down analytic models. Now we try to generate much more realistic pictures of black holes using this this code called CARBAM. And basically now you can factor in any sort of asymmetry in the emission along the ring, or any of the rings. You can factor in polarization, magnetic field lines. You can also, if it's spinning, it'll have a spin axis. You can sort of change the tilt of the spin axis. And it turns out that actually has a huge effect on the interferometric response. So it's good that we factored that in. And then you get these sort of crazy phase plots, which Alyssa calls psychedelic. But you can see that even, there's a huge variation along the angle of inclination, but if you just sort of settle on one angle of inclination, I have 17, 30, and 60, from one box to another, this is increasing the magnitude of the spin. You can see that the phase still varies between the two, between the three, and this is true for any angle that you pick. It's also true that if we just focus on centroid displacement, which is probably the most noticeable effect of black hole spin, centroid, first of all, it's not the actual geometric center of the ring that we're looking at. It's more of it's sort of the center of light density or flux density. So you would expect that any sort of asymmetry or change in polarization or change in angle of inclination would displace the centroid without actually physically changing the center of the ring that you're looking at. But I included these plots just to say if what we're it's worth looking at the phase, not just to discern not just to try to pinpoint the displacement due to spin or the stretching due to spin. There are many other properties of the black hole that create similar effects, can still affect centroid displacement, can still affect other properties that would show in the phase up in the phase response. And I think it's just worth exploring. It's just worth trying to chart out so that we can make more accurate predictions and better fit models. So yeah, that's basically it. These are some more graphs that just show relative centroid displacement if you just sort of tweak around with different parameters of the black hole. Especially if you change angle of inclination and you change the mass and you give it polarization or you take away polarization, the sort of relative displacement of the centroids behaves very differently. So yeah, I just summarized, so we don't care about that. I'd like to thank my cohort, my astro homies. I love you guys. And yeah, thanks to my professors, Alyssa and Doug, and especially thanks to my advisors. It's been really, really great to work with you guys. So yeah, thank you.
So, questions?
So I think really nice talk.
think this was in your slide, but I couldn't really see it. But what do you expect to be the uncertainty on the spin measurements in the idealized geometries and then the non-idealized geometries, and how do you expect that to change for real observations?
Yeah, okay, that's a great question. I'm not sure how good my project actually is for giving you like a fixed number on how much a black hole is spinning, especially because like the whole point of adding the curve-M simulations, like these things, and especially these plots, is that like the displacement that you're trying to match depends on a lot more than just the black hole spin. So I would say that the uncertainty that I would give you is like very, very big. But at least you can probably like definitively say whether or not it's spinning at all, or like whether it's maximally spinning or not, like minimally spinning. I guess would be the main thing. Yeah.
Thank you.
That was really cool. It's an incredibly technical project. If somebody handed you Beck's data tomorrow, perfectly calibrated, would you prefer to analyze it in image space, or the phase of VUV, or in this 1D sort of azimuthally average thing that you were talking about as well?
Oh, I would, well, so just to be clear, I wasn't talking about azimuthal averaging. I was just saying, like, we're using polar coordinates since the Beck's orbit is basically a circle. So it's just like a coordinate change, but it's like the same data as if you were looking at UV plots. I would 100%, oh, sorry, yeah.
I just meant the average or in angular coordinates around the VUV rings.
The average? Oh, it's okay.
No, it's okay.
Okay, I would totally work in UV coordinates because, like, I mean, our data is in UV coordinates. We then have to, like, only at the end when you reconstruct the image are you looking at, like, X, Y coordinates. So I guess I would want to work with the raw data for sure.
I just had a question for you and the experts in the room that I asked you once before at the beginning of the semester and you didn't know, so maybe you know now. Which is like, with the existing data, have people looked at phase, like for data that you already have, just from the HT? Like, is there any information that you can already use? Do you know?
I'm okay. There is
phase information.
There is phase information.
I know, but I mean, is it useful in this way?
I think it's useful. I'm not sure that people have looked at just phase very much, so I think that was a point of the project.
Yeah, so phase is used implicitly in imaging all the time.
Right.
We aren't throwing that
Right, no,
information away.
yeah.
So these really clean phase signatures of spin show up in averaged images, and so it's the kind of thing that you would extract at the end of a repeated campaign where you resolve many dynamical times at the source, which we don't have here. And it's one of the things Beck's is promising to deliver. It's not just high resolution, but many images.
So the answer is, you can't get a hint.
Well, so the answer is that the phase information is there. It's just it's not so simple a picture because there's fine structure that isn't just the photon. Right? You're capturing a messy flow at one instant, whereas Sol's project is characterizing what you would expect on average.
Perfect. Well, thank you again, and thank you, please, to all the students because they've done such an amazing job.